Hello, my name is Constantine, but I'm currently masquerading as Liam because I cannot change my name right now.
I'm Gabriel. I'm not masquerading as anybody today.
Yeah, I'm the IEEE academic director and also one of the 3,500 TAs.
I'm the competitions director, and I was a TA.
Yep, so we're both pretty qualified for this, thankfully. All right, now let us jump in. Oh, wait.
Yeah, so the first thing we're going to want to do is download that XDC file. You want to make sure it is an XDC file type. Just put that anywhere. Maybe put it somewhere where, maybe like on your desktop or something. And we're going to come back to that later.
Yep.
I sent the link on the chat, so if anyone has any trouble downloading it, let me know.
Could you just send that link again in chat?
Oh, you must have joined. Right. Okay.
Oh,
thanks.
Yeah. I was like, re-drop it in.
Oops. Okay. There we go. Yeah, so when you open that link, you're going to see a bunch of text probably, but you want to just right-click on that page and then just say Save Link As, and then it should save it as the file type you want, which is XDC.
Mm-hmm.
All right, I guess I'll talk about this. Yep, so Vivado Design Suite is a software suite for synthesis and analysis of HDL designs. It comes with a bunch of different tools you're going to be using throughout LEC 3500. It's going to be your IDE, your simulator, and your programming tool. So it's really a multi-tool for FPGA design, and you're going to get pretty comfortable with it by the end of the semester. So, all right, let's move on. Yeah, so pretty much the main tool you're going to be using, LEC 3500. It can synthesize your HDL. It'll simulate your designs, programs your FPGA. It costed $200 million to make, and maybe it doesn't look like it, but it replaced an older tool called ISE, and older LEC 3500 students might have had to use that, maybe 3-4 years ago. The suite includes Vivado SDK, which is an Eclipse-based IDE for programming microprocessors you can build in your FPGA. It's optional to do the microblade stuff this semester, but I recommend you try it. It's really fun. Yeah. Move on. So Xilinx is the company that made Vivado, and it's an American technology company, and it's the primary supplier of FPGAs. And they invented the FPGA, in fact, and they were the first to make a fabless manufacturing model. They are the creators of Vivado. They're also the largest FPGA manufacturer in the world, with about 50% market share of the market, maybe as high as 60%. But as of October 2020, Xilinx was acquired by AMD, so they're now an AMD company. All right, so this is the FPGA you guys probably have seen the past couple of weeks. It's a Nexus A7, used to be called the Nexus 4 DDR. It's one of the best entry-level FPGAs on the market. It's really a good board. No matter how frustrating you might find working with it this is actually one of the best on the market for students. So,
Yeah,
all right.
Blame the software, not the FPGA.
All right, yeah. Yeah, so it's got a bunch of stuff built into it. It's got a microphone, accelerometer, Ethernet port. Some of the stuff you might not be able to use, but you can definitely use a temperature sensor. You can definitely use microphone.
Really?
Well, what, remotely?
Yeah, for the microphone. I'm not sure if there's a speaker to actually interact with it.
Well, I think some of them have a speaker hooked up, or they will have a speaker hooked up in the future.
Oh, so people
But last semester they had speakers hooked up to it, yeah.
Yeah, because I used the microphone for my innovation when I took this course.
Yeah, it's really fun to mess with that stuff.
Yeah, it's a lot of stuff to play with.
And yeah, because it has all this stuff that you can use, you'll probably find some interesting ways of using it remotely. So yeah. All right, let's move on. So yeah, this is the remote hardware setup. You guys probably seen this before. Looks like
Hopefully.
they've hooked up a USB to this one, so you might be able to do some UART stuff with that. Yeah, some of these have a screen hooked up to this, a PMOD connector. Some of them will have a speaker and stuff hooked up to it as well. You interact with it using a GUI. Yeah, that's about it.
Mm-hmm. All right. So these are the various types of variables or declarations that you can make inside your modules in Verilog. Just as a quick go over. One of the first types is the register type, which is used to hold and store data, mainly used in behavioral code. So how it uses that you would declare a variable as the type reg, but you can also add say like a bus width to it to make it wider, so as to get more use out of it and use it for more complex applications. And you also have integers, which is it's kind of like a reg, but 32-bit, and it's good for counting and for loops, which is what you'll probably mainly use it for if you ever do.
It's very useful too because Vivado will actually remove the excess bits. So even though you might not count up to 32 bits, it'll automatically know what you're trying to go for, and it'll wipe out the ones you don't need. So it's easy if you're counting up to a really large number and you don't know how many bits that number is going to be. So.
Yeah. And you have wires, which act as sort of like the connections between the modules you create and the logic gates. So like registers, you can also control the bus widths, but these cannot save their values, so you can't assign to a wire and expect it to hold without any input. And then you have parameters, which act as kind of like just constants. So as to say, your parameters can be things like how wide a bus is, or like how much a for loop can count up to. So there's many different applications you can use it for, and it's really up to what you need, basically.
So yeah, it's just further reading for if you want to look into synthesizable, non-synthesizable code. It's important to kind of understand that some code in Verilog will turn into hardware, some of it will not turn into hardware. And understanding the differences between what's used for what will help you out a lot. The stuff that isn't synthesized is used in test benches or other purposes.
Yeah, like the like initial locks can't be synthesized, for example.
Yeah.
Those are only used for actual like test benches, as Gabe said. All right. So files are sorted into directories, which if you want to follow along, then you can create the intro 00 directory, and then add to all your subfolders to them with your constraints and your .v files.
Depending on what you guys are working on, if you're using on the lab, if you're working on the lab computers, put it in your desktop. It'll probably be the easiest place to put it. If you're working on your own home machines and you got Vivado installed and set up and everything, you can just put it in the C directory. It sounds like a bad idea, but it'll be a lot more convenient to deal with later.
Mm-hmm. Yep. And then you just take the constraints file that Gabe linked earlier, and then just move it into the constraints folder.
Wait, could you go back just to make sure everyone got the directory set up?
All right.
Having issues with setting up the directories? So make a folder called intro _0 and then a folder within that called source, and then 2 folders within that called constraints and HDL. Okay, I think everyone's good.
All right, we can move on. All right, so yeah, just you take the file that we linked earlier, and then you just toss it into constraints.
Yep.
That will control the assignments to the FPGA between your module code and the actual board itself.
So
This is-
is anyone using their own computers for this? If
I
not, we
think,
can probably skip this part because this is just
yeah.
how to set up the board files.
I think most everybody's likely using a lab computer because this workshop was heavily advertised to 3,500 students.
That makes sense, yeah.
Yeah. So I guess we can skip that part. So yeah, if you don't know how to launch a new project in Vivado, there's an easy button when you start the software to get it working. So you just hit create new projects. And then you just you are introduced to the project wizard where you will go through setting up your project. For the naming convention, we go by like a relevant name of like what we're doing at the beginning and then a series of numbers after to say signify which lab this is. For here, we're just doing an intro, so we call it intro N00 because it's the very first and only one.
Yeah, you want to make sure that's put inside your the project file that the directory we made earlier. So you don't want to.
As you can see, we're sourcing it from the C intro 00 that we made earlier. So it'll automatically grab, like, say, the XDC file that you placed earlier. All right, everybody good? All right, moving on now. For this, you want to set it as an RTL project because we'll be working with Verilog code to synthesize a module. And for here, we'll be the adding sources part, where, let me just see up ahead. Okay. Are there sources already in the thing that they did?
No, we're creating the files.
Oh, okay. Yeah, so for this, you want to create the file, but you also want to set it as a target language of Verilog, which after you hit that, you have to choose to save it in your source/HDL directory.
Yeah, this is something I see a lot of students ignoring. This is really important to just make sure that your source files aren't within that giant project mess. You want to keep your files outside of that so you can delete it afterwards and forget about it.
Yeah, I kind of fell into that trap when I took this course.
Oh, I did too. I lost so much code, so much. I just keep overwriting the old projects, right? It just kept happening.
Yep.
So yeah, you'll notice that if you're looking for the folder we created, you'll notice that Vivado generated a project folder. You want to just sort of go to your source and make sure that you select HDL over there.
Mm-hmm.
Yeah, so first one, we're going to be naming it gate level example. And then we want to do the same thing again, but make sure that we set the file locations for each one because the default will always be the project. So we want 3 files total, gate level, behavioral, and data flow. Yeah.
Yep. Everybody got that?
I might need a minute.
Yeah. We'll give them a minute to catch up.
Is anyone behind or anything? I mean, let us know.
Or if you need something to be explained a bit more. We're always open to questions.
Also, let us know if we're going too slow. That's also a possibility here.
That can also be a problem.
I think after this, we just need to make sure that, all the file locations are the same, and we've got 3 files.
Yeah. So in the intro 00 file you created, you're just sourcing all your Verilog files.
Yeah, good question. We want to keep our files outside the project folder because we want to be able to delete the project folder if we don't need it anymore. I have a whole slide where I kind of talk about why the project folder is a bad thing to move around. You can't share it with your, with your partners easily. You can't, upload it as easily. It has a lot of junk in there that we don't want to have to share. So keeping the files that we actually care about outside the project folder helps us avoid having to deal with that giant mess.
Yeah, so just for the sake of housekeeping, basically.
It'll make your life easier. It might seem a little weird, but it will make your life easier.
All right. I think we're good to move on now. It's been about 3 minutes. All right. So after you do all that, if your files all look like this in the add sources directory, that means you've successfully added them all. And you are free to move on to the next stage, which is add existing IP, which can be useful, but we don't actually need that right now. Do you want to explain what this is used for?
Yeah, so if you're doing microblaze or anything like that, and you save that all as, or maybe even like put together your own designs, you could save it as an IP and import it whenever you want. It can make it a little bit easier to import large amounts of Verilog files without messing things up, but I didn't use it much in this course. You might not find a reason to use it, but it is pretty useful. And if you can learn how to use it, it can make your life pretty easy as well. Like if, for instance, the BCD decoder, if you make that an IP, you just import it. All the files with it just comes right in.
Yeah, if you're working with like modules that are meant to be reused across many, many projects, then the add existing IP is quite useful. You can just import it.
Exactly.
And then once you get to the add constraints part, then
I forgot to rename that. Let me rename it.
Oh.
Yeah, so it's not the master, but it's the remote default that we want, which is the one that I linked earlier. So
yeah, instead of a master, just throw in the remote default. It should be good to go. I'm not sure if it will like do a live update though, Gabe.
Don't worry about it. I'm just doing it so I don't forget.
Oh. Yeah, we'll be publishing the slides after, so.
Yep.
All right.
And you see here, I remembered.
Yeah. Oh, yes, you've actually, you updated it. Oh, yeah, so after you add your XCC file, this is what it should look like. It's used to control which module inputs and outputs are tied to the board connections. So if you want to like control it from the buttons, the switches, or the LEDs, you can. The next step, and probably the hardest one, is getting your the right board set up. This one's a real headache because look at all these numbers.
You can skip through just by clicking the boards button, but yeah, I think they imported a lot of board files in that, so you might need to scroll a bit.
Yeah. For the labs, we're using the Nexus A7, so you just hit the boards tab, and then you can search for Nexus and then go directly to Nexus A7.
I think we really need to emphasize how important the step is.
Yeah.
I've seen so many students who are just like, you know, the code synthesizes, it implements, it's just perfect, everything is fine, but then it just fails in bitstream because it's like there's no connection with this. Like there's no switch here. There's no switch here.
Yeah, I actually did that earlier. I accidentally picked the video board instead of the Nexus board.
Yeah, so, and the thing is, the violations that produces are just scary looking, so.
Yeah. This can make or break your weekend when you start working on a lab.
Okay, so.
Yep. And at the end, your project summary should look something like this.
Yep, 3 source files added. The project name is there. No configurable IP, 1 constraint file added, and the default board being the Nexus A7100T.
Mm-hmm.
All right.
And then you go through the step of initializing, and now you're here. These are where you define your I/O ports, so your inputs and outputs, and then Vivado will just automatically make a module file that has them predefined. So what you do is you hit port name, and then you type in the name of the I/O that you want. So, and then you can go to direction and make it an input, an output, or an in-out. And then if you hit bus, you can make it wider than 1 bit, so you can go up to however big you would like it.
Yeah, one thing I want to mention is don't press OK when you're done with just one file. I've made that mistake a couple times, and if you don't add any port names or inputs, the module file is blank. And Vivado will complain about it.
Yep.
So just make sure you put at least some port name for each of them before you press the OK button.
Yeah.
So we want this.
Yeah, for all the.
Oh, go ahead.
Oh yeah, so you want basically this setup for all of them. So I guess we'll just give people like a few minutes to do that. It's a bit to click through.
Yeah, so we're going to be using the same port names for each of these examples. So.
Yep. So yeah, if you can't tell, we're going to be going through the various types of modeling. So gate level, behavioral, and data flow. So if any of you guys are confused as to what these are, don't worry about it. We're here to help you.
Yeah, so if you go to the next slide, I think I just go over the behavioral example and the data flow.
Okay.
Yeah.
All right, so yeah, it's the exact same here. And then after you've successfully defined all the inputs and outputs and created your projects, you are able to determine which module you want to be your top one, which is the one that will be synthesized and implemented, and then have its bitstream generated if you want to display it on the FPGA. Gabe, you said this step was the one that people tend to forget a lot when they're trying to...
Setting the top module. Yep. Oh, always remember to set the top module that you actually want to be the top.
Yeah.
We're not going to be generating a bitstream with these examples, I think. I think we just kind of synthesize and show the design.
Yep. I have one I can show off later, like the multiplier one, because I already have the bitstream made.
Sorry, I have a question. If we wanted to like manually set a top module, how would we do that? Or is that like not covered in this?
Oh, just right click on any of the modules, and then there should be an option to say set as top.
Okay.
I think Gabe, you have a slide on that actually.
Yep. There's a bunch of slides where
Okay. Cool. Thank you.
Yep. Yeah. Eventually, one of the slides covers that part.
I think the behavioral is by default the top because it went by alphabetical order. If you get something other than behavioral, I'm actually curious to know what happened.
What went wrong? So yeah, the top module is like the root of your design. So it's what Vivado will start compiling from, and what it will look for when it's making the circuit.
Yeah, it helps to imagine the top module as, it's not just something that calls all the other modules like C code does. It actually has all the modules within it.
Mm-hmm.
And the inputs and outputs are all wired outside of the top module. So for instance, if you have an input and you want it only to go into the module that's within the top, you can't. You have to pass it through the top. It's like a membrane that sort of surrounds it.
Right. So yeah, there are 3 main ways of creating digital logic in Verilog. The first one is gate level, which is pretty straightforward in that you declare like your gates, such as your ORs, your ANDs, your NOTs, and then you connect between them with wires to make your circuit. This kind of modeling isn't really used for like higher level circuits because it would get kind of crazy to try like define every single gate.
I don't think I've ever seen actual gate level modeling code that's serious. I think it's only just for simulation and testing.
Yeah. And you have a data flow modeling, which involves like the assign statement, which is used to connect values to wires from registers or other wires. And then you have behavioral modeling, which is a lot like C code, because you're using ifs, elses, cases, and always and for loops.
Yeah.
And now we'll be applying each of one of the modeling forms to create this very basic logic circuit, which is an AND gate, a NOT, an OR, and another AND, and a NOT.
If anyone's curious as to what this design is, it absolutely is nothing. I think I just randomized a bunch of logic gates together. But applying the same thing, you can make a mux, right? So if you switch these things around, you can kind of make a mux.
Yep. And for each of these connections, you should have an idea of what the wire names are for. So this one will be named net 1, net 2, net 3, and net 4, because you'll be needing to connect the gates together. So the output of the first AND gate will need to be connected to the input of this OR. It's the same with this this NOT gate. And now you can just open up your gate level example and we can get going. And once you've opened it up, you will notice that because you defined the inputs and outputs when you were setting up the projects, they'll already all be in here, which makes it super simple. You can just jump right in and start typing away your code.
If you wanted to change your mind last minute about like inputs and outputs, if you were to just manually type them in.
Yeah, you can manually type it in. It's absolutely fine. It's just a shortcut. And it's an important step because if you don't put any inputs or outputs, this file will be blank. So you won't even have the time scale. You won't have the module name. You have to type all that out. So even if you had no idea what the module is going to do, at least put one input just so that you automatically generate this.
Okay. Awesome.
Yeah. So yeah, this is what a gate level modeling would look like. As you can see, we have the ANDs, the NOTs, the ORs, as well as like the wires that are used to connect them together. So like I said before, net 1 is at the output of the first AND. The second wire is at the output of the first NOT. And then they're both connected to the OR. Though I see here that, actually I'm not sure if you can, because Gabe, do you remember how you can do like a dot input name and then you can directly tie stuff together?
Yeah, you can, I think you can do that, but I don't know if you can do that with the AND, the NOT, and OR stuff. You're talking about named port connections.
Yeah.
Yeah, I don't know. I never tried, but this is the only format I've ever found with gate level modeling. There's not much info on this stuff, of course, because it's not used as often, but
yeah.
But I typically go for named. I never really like doing ordered.
Yeah, same. Ordered can get like very confusing fast.
Yeah, fun fact, that's a question I got on the final once.
Really?
Yeah, tell the difference between named and port connections. Which one, named and ordered, which one creates the most errors? And it's like, what? Like if you weren't like programming a ton of Verilog and, you know, just constantly cramming it, you probably wouldn't be able to even know what the question was asking.
Yeah.
Anyway.
All right, so has everyone managed to hammer away?
By the way, guys, you don't have to write down the comments. You can just type in the code. The comments are just there to sort of explain what's going on.
Yeah.
And yeah, I'll be uploading, well, the final source files later, but so you can have a look at the comments in the future if you want. So you don't have to record it.
Yeah, you can read over this code as well. In fact, like all the code in this will be published after. I guess we'll get that.
He has a good point. Yeah, that was a mistake. I forgot to fix that. Name it N2.
Okay.
It's one of those things I saw like a long time ago, but then I just didn't do anything about it. But yeah, you want a name there. Just call it N2.
Mm-hmm. Yeah, I think when I did like a year-long internship working in a digital design, I never once saw gate level modeling.
Me neither, and I'm also doing something similar.
Yeah.
You don't see it in industry, guys, so I don't know. I don't know where it's ever used. I can't think of a practical application of it. I don't know.
Yeah.
Step simulation and testing gate delays, but
There's like better ways of doing that though.
yeah, you do that in analog simulators, not digital. So
Yeah, but with the analog simulators, we use MOSFETs.
yeah, I mean, like you get better timing analysis results from that than you would from digital simulations.
Yeah, I guess so. All right, I guess we can.
Anyone
move on.
still typing away, or we good to move on? By the way, just do a Control S and maybe look out for any syntax errors you have. If it's complaining about something, look around, make sure you're not missing a semicolon. Make sure you didn't misspell any of the net names or the input names. All right, I think everyone's good.
All right.
Yeah, so you want to run a synthesis after that, and then check out the RTL analysis schematic.
Yeah. So you just you hit this button, and then once it's finished, you just open up the elaborate design and RTL analysis, and then you can view the schematic. And if everything went right, oh wait, it does not show. Yes. Yeah.
Why is that slide there? That feels like a mistake.
Yeah.
Oh, did we set the gate level as our top? I feel like that moved.
Yes,
Before
I think.
synthesis, make sure the gate level model is your top module, guys.
So yeah.
Figure
The
out
slide should be a bit further back.
Yeah, it should. I think I might have accidentally dragged this somehow.
So yeah, when you guys were like asking earlier about how to set it as top, you just right-click, go down, and hit this button.
Yep. All right. Moved it to the right spot now.
Yep. And then hopefully, if you did everything right, your schematic should look exactly like the diagram we had earlier. So we'll have like a NOT gate here, an AND, an OR, another AND, and then a final inverter. Now it's time for data flow. You can't use data flow on registers, but you can assign a wire's value to a register. So your left-hand side of your assign statement can be a wire, but the right-hand side could have both wires and registers to define the logic. So just as a note, for this particular part, you want to set your data flow example as your TB top when you go to synthesize the schematic. And what we have here is the data flow model of our circuit, which is much, much more compact than the gate level one.
I think you can really appreciate the data flow model here.
Yep.
I think it's the most compact one out of all.
Yeah. Though I sometimes like see designers also foregoing this one and just using only behavioral, but I think that's just out of habit. This one's still quite valid for design even nowadays.
Yeah, it's absolutely valid. One thing I want to point out, I've had this kind of like discussion with a bunch of students when I was TAing. Notice how we're using a tilde instead of an exclamation mark. Maybe some of you who've coded might have gotten used to exclamation marks being the not, but the tilde is actually a different operation. It's like a logical nod instead of a Boolean.
Yeah. It signifies an inversion of the signal that's to the right of it.
Mm-hmm.
So yeah, if the tilde is like right outside of a bracket, then everything in the bracket gets inverted. So that's why that's here. That's to signify the inverter that's at the end of the circuit. Right.
You might find that when you're modeling these things, it helps to just sort of work backwards, right? Start with what's inside the brackets and then, put stuff around it until you eventually get what you need.
So yeah, here you would start with
A and B.
The inverter. Or I guess, yeah, that would also work.
Or, yeah, I see it.
Because it's kind of like a pyramid, so you start from the output and then you work back. Yeah, I guess since this is only one line of code, this one's pretty quick to do, so I guess we can move on.
Just make sure there's no syntax errors, guys, and yeah, I guess we'll be good.
And if everything went all right for your schematic synthesis, it should look exactly like the data flow or like the gate level and the initial schematic we showed you. And last but not least is behavioral modeling. This one's probably the most important one that you will learn from this course because it's used heavily in industry because of its C-like logic. So the advantage it has is that it can abstract a lot of your logic design, so you don't have to write out every gate. You just write kind of like a programming description of your gates, and then it will just fill it out for you.
Oh, could you go back 2 slides, Constantine?
Okay.
So this one?
Is this one good enough?
Forward. Maybe the schematic. Yeah.
So yeah, your schematic should look exactly like the other ones.
If it looks really different or very strange, you might have selected the wrong schematic. You want the one under RTL analysis, I think, because there's 2 schematic. There's 2 schematic buttons, I think. I sometimes click the wrong one, so.
Yeah, let me just go back to the one that shows which one.
Yeah, so you want it under RTL analysis, elaborate design.
Yeah.
That's a serious UI problem I think they should address.
Yeah, that left-hand bar is just massive.
Okay, so yeah.
So yeah, for your behavioral modeling, which you should set as your top for this example.
Oh yeah, we haven't been setting as top if we're synthesizing, have we?
I also reminded them for like the data flow to do that.
Okay, awesome.
Yeah.
It's a bit anticlimactic. It's basically data flow, but within an always block.
Yep. So yeah, to avoid creating any latches, you have to take all your inputs and make sure they're in the always at statement, because otherwise Vivado will try to save the value, which will create a latch, which you may or may not want.
Yeah, that area where we have A, B, C, D, that's what's known as your sensitivity list. And you'd have all your inputs or values that are changing within it. You don't put your outputs in the sensitivity list. Also, if anyone hasn't noticed, we've changed the output from just a typical output out to output reg out, because we can't assign values inside an always block if it's a wire.
Mm-hmm. Yeah, so this one's primarily for working with the registers.
Yeah, so outputs are allowed to be registers, but inputs are never registers, I think. Yeah, no, they're never registers. They're always wires. So.
Are they never registers?
You can't have an input register, I think.
Oh, you mean in the always at?
Oh, I mean like the like in the
right-hand side?
No, at the top where we're defining our inputs and output.
Oh, yeah, you can't have an input register.
And it kind of makes sense. It doesn't really I mean, if you wanted a register, then you would just wire whatever input to an actual register within your module. So
Yeah.
basically, you
Here,
can't
this
control what you're being fed. So
this here is just kind of describing your output as being driven by register, and here is defining your inputs, the wire names of your.
yeah, good question. So using the asterisk is fine. You can typically use that, and it'll just basically tell Vivado put whatever is actually sensitive into the sensitivity list. It'll just basically leave it to Vivado to make the decision. Typically, you can do it, and it doesn't create latches. It works. It works very well, but it might make it, I don't know. I don't know if using it is good or not. I mean, I know that older versions of Vivado and ISE will not support it because that's kind of a new thing they've added. You can use an asterisk though. It works the same way.
Yep.
It's just basically telling, just pick whichever ones are actually inputs and make the decision that you need to make.
Yeah. So for example, if you only had A, B, C in here, then if D tried to change, then nothing would actually happen for out, and then D would just be held as a latch for the old value until like A, B, or C changed. But with like the asterisk, I mean, everything that's inside here, if it changes, it will cause a change at out. So it's kind of like a short form for this. Though you can't really control it if it's an asterisk, if like a different change, or like you add something there down the line.
If you actually did want to latch, in the case that you actually did want to latch, the asterisk doesn't work. You can't control it.
Sometimes you want latches, sometimes you don't.
Yeah, there's a whole debate on that, whether or not latches should ever exist, but there's some good reasons to have it every now and then. Yep. I think throughout Elect 3500 though, none of the students have an excuse to use any latches, I think.
Yep. If there's a latch, that's a instant no.
No. Throughout this course, no latches.
Forbidden. So yeah, has everybody managed to set behavioral as your top module and write down the always at?
Yeah, I think everyone should be good. Just I guess we can move on. You just need to run a synthesis on that.
Yep.
So same deal, set the behavioral model as your top and then run a synthesis on it.
All right, and it should look the exact same as your other schematics. All right, now here's the fun part, the for loops. So do y'all see this the circuit on the right here? If you tried to implement it, you'd have to do a lot of assign statements, like at least 8, to actually get everything all wired up, and it would be like crazy hard to keep track of all these wires. And especially with like gate level modeling, this one would just be absolutely massive.
Possible.
Yeah. And even with like a normal behavioral without for loops, this would be like a lot to deal with. But as you can see, a lot of it just repeats over and over. So if we set up an always loop with a for loop inside it, then we can take advantage of that and produce this complex circuit with a very small amount of code. So what the circuit does is it's an unsigned multiplier. So it takes 2 4-bit numbers, multiplies them together, and outputs an 8-bit number. This here is just a bit about the theory of how the multiplier works with the for loop. So here, Z pause is your the output. So we just it's going to be like unsigned always at, and we initialize it to 0. So that's this output part here. And then we have a for loop, which here you have your I, which is an integer that starts at 0, and then it goes up to the to the amount of bits wide that you're multiplying. So while I is less than 4, so it'll go from 0 to 3, and then it'll increment by like 1 each time. And so how it works is that you have 2 to 4-bit numbers, your multiplier and your multiplicand. Here in this case, x pos is the multiplicand and y pos is the multiplier. And the multiplier's bits are all ANDed with each one of the multiplicands while being shifted by a certain amount. And the shift amount is determined by the place that the multiplier is at. So here it's being ANDed with the 0th bit of the multiplier, so it's not shifted at all. Here it's being ANDed by the first one, so it's shifted once. Here the second, so it's shifted twice. Here's the third, so it's shifted 3 times. And you can kind of see that here. So you start by taking this x pos and saving it to like a temporary value. So that would be here. And this only occurs if your multiplier is 1 at that point, because then at this point it would just be 0 and there's no partial product to add together at the end. And then you shift it a certain amount to whatever the multiplier was at, and then you add it together, and then you keep doing that until you've gone through every single bit of the multiplier. And then next slide, we can see the entire circuit. This one you don't actually have to write down. This is just a bit of an explanation.
What I want to bring up is, I think it's important to sort of mention, for loops, they don't work the way they work in C. They're more like macros that kind of help you instantiate a bunch of hardware.
Yeah, because if we go back here, as you can see, it's we're taking advantage of like the repetitiveness of this type of circuit, so we can instantiate like multiple things of this with very little code. And so yeah.
Yeah, closest thing to a for loop in actual Verilog is a finite state machine.
Oh yes.
So
yeah, we'll be publishing this after if you guys want to like take a look at it. It's a bit more of an advanced circuit, but it's a good thing to know. All right, Gabe.
all right. So on to a more complex and interesting design. So this was one I put together a while back. It'll basically do a bunch of different things, like it'll take control of all the LEDs on the board, flash them, or maybe, what's it called? Shift across. And I made a new one called the Randomizer, which is new. And this one will basically output a random binary sequence. Pseudo-random. We'll talk about that in a bit later. So yeah, let's move on. So the first thing we're going to want to do is, in the same project, we want to add a new source here. So we're going to kind of build off the old projects. We're going to keep the old modules and maybe just keep them in the background. We're not going to use them. But we're going to build this whole, sorry. Yeah, where will the slides be posted? Yeah, that's a good question.
They'll be in the IEEE Google Drive, but I'll also share a link in the Teams chat so that everyone can just view them after.
Okay, if they're not in the Teams chat, maybe we should just send a link now, or I don't know.
I don't believe the slides are set as public right now because they're currently in my personal email.
Okay, that makes sense. Okay, yeah, so.
Yeah, we can figure that out after the workshop.
Well, he has the older version of slides.
This here we have we've added stuff to this, like the multiplier circuit. The old slides don't have that in it.
Also, the constraints file has changed, and a few other things had to change as well, just so that you can control it remotely. So yeah. It's a bit of a different. It's a bit different than the slides that are posted on the CLearn page.
Yep.
But
and the pseudo random generator is also new.
Yeah, that's new too.
Yeah, those things are good ideas for if you want to like incorporate them into your innovation for Lab 9 in some way.
Oh, you could absolutely use it. When I was teaching, a bunch of students used the flasher, for instance. It was for the alarm, right, or the egg timer.
Yeah.
Okay, so yeah, so let's just move on. I guess we'll post the slides. Can we post them on the IEEE page, maybe?
On the Facebook page or the website?
On the Facebook page.
Yeah, I can do that.
Okay, we'll do that after. We'll post it on the Facebook page, so watch out for the IEEE Facebook page.
Yeah. I'll also post a link in the Teams chat, so just keep an eye out.
Okay. So yeah, first thing we're going to want to do here is we want to create a clock divider. We're going to be using this clock divider for a bunch of different things, and you are going to be using a clock divider later on in the semester as well. So this will be a very important module to have.
Yep.
So we're going to want to name it clock divider, and we want to make sure the file location is the same as it was earlier in the HDL folder that we've made earlier.
So yeah, so C intro 00 source HDL.
Or if you're working on the computer, it's the desktop. So
Yeah.
okay, yeah, we can move on, I think. So we want to instantiate all these modules. Well, sorry, create them, create the files. So we want to create a clock divider, a shift, a flash, a randomizer, a mux, and a top. So we'll keep this up for a bit. Tell everyone.
So yeah, basically just repeat what you did before, but create the rest of these .vs.
This part's a bit repetitive, but
Yeah.
it saves you a lot of trouble later.
Yeah, it all comes together in the top module where these all get combined.
Yes, all these are actually part of the same design. So
Yeah, for your innovation, you'll be working with you'll be combining your already pre-made clock design and then adding something onto it.
all right, I guess this will take maybe 2 minutes.
All right, so I guess at 2 p.m. we can keep going.
Yep.
All right.
And I think after we get through some of this stuff, like the grindier stuff, we can actually start typing the code in, and it should move a little faster.
Yeah. I guess we can share the GitHub repo and then let them just copy and paste.
Talking about the code?
Yeah.
I haven't put it up yet. The changes anyway. I had to make a couple changes, so I'll need to go and fix that. Well, there isn't much to type out. On average, is like 20 lines of code that they need to add. The randomizer is very short.
File?
Yeah. I think the clock divider was the longest thing.
Yeah, it definitely is.
But it's the most useful thing, so. And we'll get to use integers.
I think enough time has passed unless anyone's still going.
Anyone still creating the files, or are we good to go? I think we're good to go.
All right.
Okay. So first thing you want to do is open up the randomizer and set these ports. Again, be careful. Don't press the OK button before you've finished all of them. I've done it many times. It's really frustrating.
Yeah. So for your randomizer, you want clock and reset as your inputs, and then for your output, you should label it LED and then set the bus width to 16 bits wide, so 15.0.
Exactly, yeah. So we want to output our design to all the LEDs. So that's why it's 16 bits. There's 16 LEDs total.
Mm-hmm. All right.
Yep.
Let's get that. If we actually end up going too fast, let us know, guys, and then we can just quickly go back and show you.
So shift is very similar. You got the clock reset, but this time we have a select, and we also have the LED output. So it's the exact same as the randomizer, just the select is added under the reset.
Mm-hmm. Right.
So the top is going to have basically every possible input and output within it. So we're combining everything together. We want a clock, a reset, a shift select, and a function select. But wait, the function select is now 2 bits. I forgot to fix that.
Okay.
Yeah.
So you, this one you just hit the bus one and then put MSB to 1, so it's 2 bits wide now.
Yeah. So you want the function select to be 2 bits. So make sure to tick the bus. I think if you tick the bus once, it'll automatically do it. Maybe not. But that's a thing that can be easily changed later anyway. So if they have to.
All right.
So.
All right, moving on.
So the mux, we got the select, the A, the B, and oh man, we got a C now too. So forgot to change that as well.
So yeah, A, B, and C, and the select should also be another bit wider, right?
Yeah, yeah.
So yeah, the main reason why we had to expand this was due to the addition of the pseudo-random number generator. So you can display all of them at once on the board.
The
So
unfortunate side effect is now we have, you know, the 4th state, which is blank.
Yeah. So yeah, just to reiterate, it's a 2-bit wide select, and then A, B, and C, and then your out is as normal. All right.
I think the out becomes a bus later anyway, so yeah, it's fine. We'll fix that later. So the clock divider. Yeah, this is where we take the minimum possible clock of 5 megahertz, and we divide that down to 2 hertz.
Yeah, the 5 megahertz clock is sourced from the internal FPGA's clock, right?
And that's as slow as it gets. It can't get slower than 5 megahertz.
Yeah.
Before you run into some serious failures, so.
Yeah,
We're gonna talk about a little bit about that later. Yep.
Yeah, I was doing some stuff with the multiplier earlier, and originally it had a clock, but I was getting some weird behavior because it was so slow.
Oh.
So I had to axe it.
Yeah, you might need to give it a faster clock.
Yeah. But then it becomes too fast to see what's happening on the board.
Well, I guess you can always assign it to a switch.
Yeah.
Tick, tick, tick. I think one of the labs force you to do that. And Vivado doesn't like it, right? Because you're saying treat this switch like a clock. It's a big no-no, apparently. Okay.
And then we have the flash module.
I think it's the exact same as the randomizer. It's clock reset and the LED bus.
So yeah, just to reiterate, it's your inputs are your clock and your reset, and then your outputs are your 16-bit wide LED. And I guess for this one, you should set your top as your top module now, right, Gabe?
Yep, that'd be a good idea. There's no code in it yet, but it'd be a good idea to do that in advance. So.
Yep. You just right-click on this one, set as top, and then whatever was on before, it will switch to it.
It just makes sense to make the top module the top module, you know?
Mm-hmm.
Okay, so this is a little bit about the clock divider. The main idea is that we're slowing down an input frequency. You know, the diagram kind of explains it pretty well, but we're actually doing a lot more than just halving the clock speed. We're dividing it by like think 200,000 or something. So we actually want to shrink the clock speed a lot more. So the whole idea of it is to just count. It'd be like if one guy in the other side of the room is counting very quickly, and every time he hits 10, you count up 1. So that's kind of the idea.
So yeah, after a certain amount of the input clock cycles have occurred, then you'll have a transition in your output clock. Yep.
And it's your clock divider.
Mm-hmm.
This might look like a lot, but it's not too bad. The first thing you're going to want to do is you want to make sure your output is a reg. So automatically, I think if you open up your clock divider module, you're going to notice that it's just an output clock 2 Hertz. So you're going to want to make that an output reg clock 2 Hertz. The equals 0 is interesting, and I think we could probably talk a little bit about that. It's usually good practice to make sure that your registers are all, what's the word? It's not initialized, but I guess
They're
initialized.
set to a value.
Yeah,
Because currently, when you power it on, they'll be in an unknown state. So until you hit the reset.
This is kind of like a macro to say, hey, please clear these registers first. Don't just use whatever's in there. Kind of matters.
Yep. When you're actually like making a circuit, though, not like an FPGA design, you'll want to always have it set up so you hit your reset at the start.
Yeah. Yeah, I think this is just an FPGA problem.
Yeah, because when you power on any device that's a circuit, you can't guarantee that your, say, finite state machines inside will be in a state that you want them to be in, so you need a way to set them.
Oh. Did everyone copy that?
So we can also take like a 5-minute break, just so everyone can copy this down, because it's a bit long.
Yeah, yeah.
All right, so I guess we'll reconvene at about 2:15.
Yeah, I'll stick around if anyone has any questions.
All right, I just have to quickly take a bathroom break.
Well, we've got just the end of this module. Well, sorry, we got the clock divider. We got to put all the modules together. After that, we're done. So I'm going to estimate maybe an hour, maybe an hour and a half. We didn't record. Oh, wait, is it recording? If it is recording, then yeah, we'll be posting the recording. I think Constantine is recording, in fact. So. Awesome. Let's see. I think it's just an unindented end. Oh, wait, no, maybe you're right. Let me see here. You're talking about the end there? Well, like at the very end of the module.
Oh yeah, there's an addition to the module, as well as like we also have a discussion on system Verilog at the end. That's not in the old slides.
Hey, Constantine. Somebody says there's an additional end here. Do you see it? Well,
In
the
the
else
circuit.
statement, the else statement should have had a begin and an end there. I didn't put one there, so that else is
Oh yeah, that's
on
that's
2
fine.
hertz. That's fine, but all right, no problem. So yeah, no, I don't think there's a missing end. Otherwise, it would have had synthesis errors. So this will synthesize, but yeah, the only thing I would add is the else. Add a begin and end for it, even though it's one line. It's just good practice.
Yeah.
But else statements or if statements can work with just one line without a begin and end. It'll just assume what's under it is,
The only
the only
statement.
thing. Yeah. So if you write another statement right after the else, it'll assume that that's outside of the else statement, and that's bad. You probably don't want that to happen. Yeah, I think people should be good by now.
Yep. If is anyone still writing? Or
Let us know if you have any syntax errors or any complaints. We can kind of go through them. If
I don't know if anyone else has this, but it says that I have a syntax error in your end module.
what does it say if you hover over it?
It just says syntax error in your quote-unquote end module.
So it's probably just a missing end or a semicolon.
Yeah, probably. Thank you.
Did you see it?
That's also what I was getting. I added a begin after the second else, and then that
Yeah.
fixed it.
Yeah. Oh, really? I added one behind the second else, and it's still there. I'll just look at it.
Can they share the screen? Maybe sharing the screen would help.
Yeah, sure. Can you see what I'm saying? Cool.
Let's see here.
Do I have to stop sharing?
I think you might. I don't see her.
Oh, okay. Then don't worry about it. Don't worry about it. I'm sure I just copied it down wrong or something. Okay, thank you.
Is this the same as what you had before, Gabe? Or did you make changes to this?
Wait, I'm just trying to open up your screen there. Nuge is saying he doesn't have any syntax problems. Sorry, Zoom is messing up here. I think I need to reset. Okay. I think we're okay. Sorry, you're talking about the clock divider?
Yeah. Did you make any changes from like last year's workshop?
No, it's exactly the same, I think.
All right, then code should be fine.
Yeah, I think it works.
Yeah, I don't see any missing beacons or ends. So it's probably like something misplaced in your guys' codes somewhere.
Yeah, probably. I'll look through it. Thank you.
Yeah, I found my mistake.
Well, what was yours? Was it a begin and end or?
I was just missing the if statement in the middle.
Oh, one whole if.
Well, that could cause some issues. If you'd like, just maybe take a snipping tool and just sort of screenshot this slide here, and we can move on to the next part.
All right, we'll give that like another 30 seconds-ish.
Okay.
So how's everyone finding the workshop? Are we going at a good pace, or do we need to speed up?
It works for me. Thank you. Also, I found my mistake as well. I just was missing an underscore, so.
Okay.
Okay.
Awesome. Well, that's good to hear. Okay. All right. So, yeah, I think everyone's good.
All right. Now on to the LED flasher.
So just to sort of talk about how the flash is going to work, we are dividing the frequency down because if we flashed the LEDs at 5 megahertz, you wouldn't see any flashing. It would just be would be very dull. So the reason we're using the clock divider is that we can flash it at a rate of 2 Hertz. And I think even 2 Hertz was a little too fast, so I think we ended up slowing it down there too. 2 Hertz was good for the others, but it, for the LED flasher, it had to be slowed down even more. So within the LED flasher, there is some extra slowdown, and we'll talk about that in a bit. So go. So yeah. Yeah, that's the problem with the flash module. I wish we kind of made this a bit simpler because, yeah, the problem is we kind of added an extra clock divider within the flash module that, slowed it down by about 3 times. So that's why the flash delay is set to 3 there.
So yeah, at this point, it's like less than 1 Hertz speed.
Yeah, it would be like, 2/3.
Yeah, like 0.66 Hertz.
Mm-hmm. I think when you tried it with 2 Hertz, it was just annoying. It was just blaring.
Yeah.
Which you might want for an alarm clock or an egg timer, I guess, but. But yeah,
Yeah, a lot.
Oh, sorry. Go ahead.
Yeah, a lot of these modules are like a general purpose. So if you have like an idea of like reusing it for something else, you can go and take inspiration from it, so to speak.
It's one of the things I like about Verilog is everything is so modularized, I guess you could say. You
Yeah.
can just take this somewhere else, put it somewhere else, and it should work fine. Whereas with C, you've got all kinds of library dependency issues and all that stuff to worry about.
Yeah, you have a lot of overhead to deal with.
I guess you can have that with Verilog too, but you'd have to have large designs to start seeing issues there.
Mm-hmm.
It's like missing module.
If you're at a point where you're missing a module, then something's gone horribly wrong. Because I remember, for me, it was usually like a parameter was missing somewhere, and then I had to go like hunt down the file that had it.
The most common thing I've seen was misspelling the module in the when you're instantiating it. So then Vivado will be like, well, I don't know what this module you're referring to is, but I know this is a very similar name is being used, so I'm just going to not use it. Now, does anyone have any issues understanding what this module is doing? I think maybe people are just typing it out. Oh, look, I actually didn't forget the else begin end at the bottom there this time.
All right, perfect.
All right, I think we're good to go. Unless anyone's having any syntax issues.
Is everyone still writing?
Anuj wants a summary. Yep, so a summary of what the Flash module is doing is we want to turn on all the LEDs at a specific frequency. So it's just, on, off, on, off, on, off. It's the only reason it's a little bit more complex than it should be is because the 2 Hertz frequency we're feeding into all the other circuits is good for them, is really good for them, but it's really bad for the Flash module because at 2 Hertz, it's just too fast.
Yeah, it's twice every second.
So it gets really annoying to look at, and it's not very nice. So what I've put together here is to just sort of divide that by 3. So we're putting a little mini clock divider in there, which is just a register that counts up to 3. And once it reaches that 3, it inverts the signal. So that's essentially what we're doing here. The actual flashing is happening there where LED Should we talk about the non-blocking operators? I just realized we kind of.
Oh yeah, there's a.
Yeah, I just realized we haven't maybe mentioned the non-blocking operators. So in case you guys haven't reached that in the course yet, the non-blocking operators are like saying equal, but equal with no order. Like let these two things happen at the same time. So you see we're resetting. We have flash delay, less than equal 0. That's not actually less than equal. It's just saying flash delay and LED should be set to 0 at the same time. But if you put just an equal, it'll do, okay, we'll do flash delay first, then we'll do LED. It's bad. We don't want that to happen.
It's not always concurrently, it just means it doesn't matter that flash delay should happen before LED. So it just means it should happen in the same cycle. Like timing wise.
I think in general though, unless you're in a an always A, B, C, D situation, you should always use a non-blocking operator.
Yeah.
There's very few cases in this course where you'd use an equal sign, I think.
For like the multiplier, you have to use a blocking operator, so the equal sign.
Okay.
You need sequential logic.
Oh yeah, that makes sense there. But I don't think anywhere else in the course used it.
It really depends on what you're doing.
I guess to be safe, if you don't know whether you should use an equal sign or non-blocking operator, just use a non-blocking operator. It'll probably be your safer bet.
That's a good default.
Yep. All right.
And I also believe that it's a proper practice not to mix non-blocking and blocking statements together, because that just mucks things up.
Yeah, I can imagine.
And Vivado will just complain about it. All right, I think we're good to move on now.
All right, let's go. So I think the next module, so yeah, this just sort of talks about the flash module. It'll flash at a slower frequency than 2 hertz, 0.66 hertz. Okay. So the LED shifter, this will be using an extra switch, and when you flip the switch, it'll change direction. So yeah, I think I mentioned this design's a little bit more complicated, but it's actually way shorter to copy. So, so I'll explain it a little bit here. Oh yeah. So it follows a similar procedure, I think. Yeah. Make sure that your output is a reg. I think in the last couple, it should be a reg, so make sure you can go back and make sure the reg is, otherwise, yeah, you'll have issues. We have a shift count here, register that we're instantiating, which is just 4 bits. Just a counter that watches which LED's on at any given moment. Basically, while it's sliding across, it'll know, oh, it's right there. Our reset logic will reset the shift count to 0 and our LED to 0. And if our shift count is, 15 or more, we want to reset our shift count. So basically what we're doing here is we're making a counter that just goes up to 15 and then resets.
Yeah, this here is I believe it's called a ternary operator.
Yep.
Which you can tell by the question mark.
That would be the equivalent of having an if-else statement.
Yeah,
I contemplated changing that to an if-else statement. It would have been easier to kind of read, but yeah, all the magic is happening in that line of code.
Yeah, and then the format is described here in the comments, which you can look at later as well.
I left a large comment there because there's kind of a lot to unwrap.
Yeah.
The basic idea of what we're doing is, if you know about binary shifts, if you have, your 0 bit and your 1 bit and then your 2 bit, if you left shift a 1 at the 0th bit, it'll just move across the LEDs. Anyway, that's what we're trying to achieve. And the ternary operator controls whether we're left shifting or right shifting. Oh no, sorry. It's controlling whether we're left shifting a 1 or right shifting a 2 to the 16, a 2 to the 15. And the 2 asterisk asterisk 15, that's just 2 to the power of 15, which is your maximum value. It'll be your 15th bit, yeah. So I guess if select is, not on, we'll be going from 1 and then just moving across to the 15th. But if we want it to go the other direction, we got to start from the max value and bring it down to 0.
Is everybody cool with understanding how the shift module works? Because this one's actually it's a pretty good one to know.
Yeah, there's a couple cases where you can definitely take advantage of it. I can see a few of the labs would take advantage of binary shifts.
Yeah, because it's like especially important for stuff like serial or parallel to serial converters.
You also use it a lot in C. You can't avoid it there.
Yeah.
I think everyone should be good. There was less to copy in this one, so.
Yeah.
It followed a very similar format to the previous one, so.
Is anyone still writing down?
Yeah, could you give me a second? Sorry. Almost
All
done.
right.
Sure.
Yeah, go ahead. Yeah, you're always at loop with a pause edge clock and a pause edge reset. You're going to be seeing that a lot because that's your most common type.
That's known as an asynchronous reset.
Yeah.
That was also a question I think I got in either the midterm or the final. And well, yeah, I think you definitely should have seen that question around.
Yeah. Thomas is asking, could you explain the LED shifter statement again?
Oh, we're talking about, okay, yeah. So select, notice how we're going LED less than equal select. So the less than equal is we're assigning the values. That's essentially the equal sign that we're using here. Select is a value that we're giving. It's a switch that we're inputting. So it's either 0 or 1. When select is 0, the initial statement there before the colon is what happens. But if select is 1, the 2 to the 15 statement applies. So the colon is like the separation between the if statement and the else statement, if that makes sense. Where's the other way around? No, if select is on, then the first statement happens, else the 2 to the 15 happens. So it follows an if-else pattern.
Yeah.
And the question mark's a ternary operator. So you can essentially replace this with an if statement that says if select, LED equals to 1 binary shifted by shift count. Else, the 2 to the 15, LED equals 2 to the 15 shifted by shift count to the right. So yeah.
Sorry, I finished copying as well, so if everyone else is done, we can move on. Sorry.
No worries. Okay. I think we're good.
So last call.
Make sure you got no syntax errors, guys. If there's anything, yeah, just let us know. All right, I think we can move on. Now we're going to get a bit random. So this one's a new addition. It's kind of a fun little thing to put in, and you might have some fun with this. I found this really interesting. So you might have heard this in your C courses or maybe in other courses that computers really don't have the ability to do things randomly to an extent. You kind of have a pseudo-random bit sequence that you can almost predict if you had enough of them. The idea of having a pseudo-random bit sequence is it's repeatable. It'll overflow back and it'll continue to be random, and it won't ever enter a dead state. So this is really interesting because the initial value matters a lot when you have a pseudo-random bit sequence. you want to start at a value of 10, maybe something else. But if you set it to 0 or 1, your actual like your bit sequence would just be a series of zeros that keeps repeating, which is no good. So yeah, what we're going to be doing is creating a shift register, and we're going to be attaching a pseudorandom bit sequence to it. So it'll kind of look like that diagram over there, but the PRBS out that's displayed isn't what's going to be our output. Our output's going to be all the registers. So we're going to be viewing all the registers at any given moment. All right, I think we're good. So I found this document by Xilinx, actually, which is really cool. And it described what registers you wanted to XNOR in order to keep a pseudorandom bit sequence. And you can get n equals from 3 to, I think, 256. So you can keep creating larger and larger pseudorandom bit sequences. I picked 16 because we have 15 LEDs, and I wanted to keep it pretty close to that. So you'll notice in this table, what we have to do is we have to XNOR our 16th bit, our 15th bit, and our 13th bit, then our 4th bit. And we want to shift that output to the first bit, basically. So like at any given time, we're XNORing those bits. We're getting the value of it, computing it, and then we're putting it back to the beginning. So it's kind of like we're taking something and then we're just shifting it to the front. And this keeps going on and on and on. And eventually, your sequence will repeat. So this is useful in computing because we can keep repeating these pseudorandom bit sequences, and it's predictable. And I think that's, yep.
Yeah, that's also a downside in that it's predictable, so it's not true random.
In some cases, you want true random. In some cases, you want random but predictable. So
yeah.
But yeah, if you want true random, it's not really possible unless you have some external source generating.
If it's like security level random, you don't want the predictable random.
That's why there's something called lava lamp encryption.
Yeah, is that like the temperature of the CPU?
No, I think it's like an actual lava lamp hooked up to something.
Oh.
Something ridiculous like that. I don't know.
Yeah,
But,
I heard like a lot of computers, random number generators are determined by the processor temperature. Because
it's actually pretty good.
It's one of the easiest random things that you can have just on board.
Yeah, so, okay, so the randomizer is a pretty short module. We got the same things, but you'll notice that in this case, we don't set our LED to 0. We set it to something other than 0. And in this particular case, you can set it to any value between 0 to 127. Actually, no, you can't have it 0 or 1. So 2 to 127. So pick your favorite value between those values. Maybe your last 2 digits of your student number or something like that, if it's not.
And that's like a decimal value, right?
Decimal, yeah.
Yeah.
We want it to be something between 0 to 127. 2.
So notice the D in front of the numbers. That's very important for telling the Vivado what kind of number you're using. Because you can input like, because you can also do this in like hexadecimal format or octadecimal.
Sometimes Vivado is smart and realizes that you're trying to go for a decimal value, but it'll still complain about it. If you have 120, that can't be binary, right? But if you have the number 11, well, that's either binary, hex, or decimal. So
yeah.
And 11 is not equal to 1, 1, which is 3. So, and you also, maybe you've noticed in some docs that you can put a number before the apostrophe. Like you want to say 10-bit 120. You don't actually have to do that. It's kind of like the asterisk. It's a shortcut that you can use to avoid having to remember how many bits the register is all the time. And Vivado is usually smart enough to realize that you mean the whole register size if you do it that way. Okay. And yeah, so pick a number between 2 to 127 and set that as your initial the output reg. And then you also want that to be a reset value as well. Now, yeah, the reason this is important is if we set that value to 0, your PRBS won't work. It'll just be a stream of zeros in an infinite loop.
I just have one question about this, Gabe. Do you see
Yep.
your, do you have your concatenating here?
Yep.
And you have like the whole previous LED value right here.
Yep.
Yeah, but then you're
Is that
your
14.0? That's actually 14.0. I think you're right. That's supposed to be 14.0. Let me
15.0 is just full work because it will just cut out that last bit anyway. Because LED is too small to hold like all of them.
yeah, so I think what happens is it just pushed out anyway, but I think 14.0 would be a smarter thing to put there.
Yeah.
I just realized that.
Yeah, I looked at it and like part of my eye was like, something seems fishy about that.
Yeah, you know, the thing was I made that mistake initially, and then I corrected it, but then I changed the design because originally what I had was 15 different PRBSs, and they're all hooked up to, you know, an output. But that was way too much to type down, I think.
Yeah.
I think everyone here would not have had a good time, so.
Yeah, that'd be a lot of flip-flops in Saint
Too much. You'd need 15 7-bit registers minimum because PRBS 7 is like a good. It's like a, you know, it's enough randomness. There's 127 possibilities there. With what we have here, I think we have a bit more than 127. I think our sequence is quite large, so. But you'll notice repeating. Like you'll notice it repeating. It's not forever.
Yeah, did it state how large the sequence was in like that document you found?
Well, it'll be 15 bits.
Yeah, but there's also a feedback.
Yeah, so the way it works is with PRBSs is it's like the max value of it. So like PRBS 7 is, you know, 127 minus 1, I think. It's like a 2 to the n minus 1. That's how you calculate how many unique values you'll get before you repeat.
So then it'll just loop back over again.
Yep. So in this case, we have 2 to the 15 minus 1, which is, you know, a lot of different sequences, but.
So has everyone had a chance to copy this down? Or you guys still writing it out? All right. I guess we can take that as a go ahead because this is pretty short.
Yeah, just make sure your XNORs are correct and that you're concatenating the right values.
Yeah, it's the tilde operator plus the hat.
It's like a baseball cap operator in total.
Oh yeah, it is like a baseball hat. Never made that connection. Gabe, I'm gonna see that from now on, whenever I look at an XNOR.
Yeah, no, I can't unsee it now.
All right.
So we now have a bunch of the modules all set up, and we're almost good to go. But we are missing a mux, and in this case, we need a mux that'll take in 3 values and output one that we want to select. So the original design was really simple for the mux, but we had to change it this semester because we now have 3 different outputs instead of the 2 from last year. So yeah. Let's then move on to the next part. So we're going to go to our mux here, and we're basically just going to do this, where we have a behavioral model for our mux, and we're going to have 4 inputs, A, B, C, D, and the select. And then we're going to output one of them based on the select value.
So yeah, this basically controls which input is tied to the output. So you can switch between which module that we just had. So you can look at all of them depending on which select is active right now.
What does the size prefix mean in the brackets that define
So-
how many classes?
Yeah, so that's like the parameter. It's a custom value that you can assign to different pieces of hardware, and what it'll do is it'll make it so that the size is anything we want it to be. We can pass it in as an extra value.
Okay.
So it's not synthesizable code, but it essentially changes the hardware.
Okay.
Yeah, it's so that you can reuse this code, but for different sized muxes.
Yep. So for instance, if we don't have a situation where we need a 16-bit mux and you just want it to be a 1-to-1, or maybe a 4, like a size of 4 bits, you just change the size parameter to 4. You just pass it in as a 4.
Cool. Thank you.
Yeah, and for here, you don't have to include this, but Gabe here set an equals 16, which means it will default to that value. So if you just declare it as a mux, it will just normally start out as a 16-bit mux.
Yep.
Oh. And here we just have behavioral that ties the output to the different inputs depending on the select using a case statement. And then we have a default, which is just kind of like the get out of jail card, so that you don't have unknown behavior.
Yeah, one thing that's kind of unfortunate is because we don't have 4 different possible outputs, we're basically grounding our 4th possible option. So I guess it's unintentionally a way to turn it off if you want to turn it off.
Yeah, because if you didn't have that, then you get into the case where like your behavior for your FPGA is unknown, so you can't guarantee what it will do.
When that happens, Vivado will do one of 2 things. It'll silently delete 90% of your design because of it, or it'll give you 100 errors.
Sorry, do you mind repeating that? When would that happen?
Vivado will do one of 2 things if your code isn't correct, or
Or
there's
if it's like,
something weird that can happen. It'll either it'll silently delete 90% of your design, put it as like minor warnings. It'll synthesize, generate a bit stream, and then you put it in the board and it does nothing because Vivado is like, yeah, none of this is going to work, so we're just going to delete it. Or it's going to give you a bunch of errors and say it's no way, and it's just no way it's going to work. So, and sometimes it'll give you more errors than you can understand and like piece together. Sometimes it'll complain about stuff in other modules too. So if this mux was wrong, it'll complain about other modules because the mux is wrong. But it always helps to understand the warnings in Vivado. If you can kind of look at the warnings and try to piece together what it's complaining about, it can help debug a lot faster than writing a test bench.
yeah, if you go through the logs, generally it'll tell you kind of what line or signal at least is causing the problem.
Yeah, if you start early on and trying to figure out what the messages mean, you'll have a better time later on.
So is everyone excited to do their Lab 9 eventually and make something innovative that will possibly get you a job?
We'll apparently get 5 extra % in the course if we win the competition. So
Yep, it's worth doing. It's worth doing 100%.
Yeah, you're talking to the guy that's running it.
well, I sure hope you like my design, whatever it's gonna be.
We'll see. We'll see.
Yeah. if you take like inspiration from this and you do something that's like really interesting.
Yeah, I'm going to try and make sure that we'll have some, corporate sponsors show up, maybe some EDA companies. I remember, before I took the course, we had a sponsor from Ross Video and I think Nokia. And a couple of students actually got co-op offers right after, so. Definitely a good, it's a really fun competition. One of my favorites.
Wait,
Yeah.
wait, wasn't 1 year you got there was a prize for FPGA? You got an actual FPGA?
Yeah, but unfortunately, it was an old FPGA that you can't use with Vivado anyway. So you got to use ISE with that one, I think.
Oh wow, they scammed him.
But during that semester, they were learning in ISE, so it was perfectly fine.
Yeah.
The only problem is if you actually wanted to use Vivado, it wouldn't support it.
Yeah, Ralph Mason was like, well, not going to need this next year.
He said it was an egg timer. What does that mean?
Well, you know those timers that you like twist that are shaped
Yes.
like an egg and then you just leave it?
Yeah.
I mean, essentially that, but in digital form.
Yeah, it'll count down from like a certain amount of time, so it could be set to like 1 minute or 2 minutes, and then it'll count down to 0.
So yeah, you need a user interface to set it, and then you need a user interface to start it, you need a user interface to stop it, and reset it when you're done.
Okay.
You'll also be using the segment displays, so it needs to count down like a clock.
Yep.
Oh, like with the numbers.
Yep.
Okay. So is that why they got us to write code to get those numbers to work in the first Verilog lab?
Yeah, you'll be using that for like the rest of the labs.
You want to make sure it's nice to work with, otherwise you're gonna really have issues.
Alright.
What have people done like in like past years for like the innovation part of it?
Well, back when I did it, I hooked it up to the Ethernet port and made my stopwatch communicate with a Python app that I wrote on another computer. That was a fun little innovation, and it wasn't terribly complicated, but it took a lot of time to figure out and piece together. I'd say most of the best, funnest innovations are ones that use the microblaze processor. So that'll force you to have to write some C code, but it'll definitely, help you out a lot.
And it's also you get like major points for being innovative, so doing something that other people have not done. Like for example, I used the microphone to do sort of like a DSP, so I analyzed sound waves coming in, and then like I calculated like the frequency, and then it would cause like the LEDs to bounce up and down based on the frequency level. So when you like put music up to the FPGA, it would like do the whole like boombox sound thing. It was really cool.
I seen one guy, he actually made it so that you can set the alarm based on the microphone. So you can place something to the microphone and it'll store it in RAM or something. And then it'll play it back as the alarm sound.
Oh really?
Yeah, it was pretty crazy.
Oh, I think I heard about that actually.
Yeah, and apparently it wasn't that complicated, but yeah, it was definitely cool to see.
Yeah, because it's just saving into registers and then figuring out how to play it back. Is there a speaker?
I think everyone's definitely copied this by now, right?
Yeah.
I think we're good to go.
All right, let's move on. Oh, this kind of explains what we went over earlier. So yeah, for this, the default parameter that we made is 16 for the size, so it'll cause A, B, and C to be from 0 to 15, and also the output as well.
All right, so now we got to create our top module. So your top module isn't going to look like this right now because there's nothing in it, but when we're done, it should look like that. It should have everything that we've created right under it. So in our top module, we're basically going to call everything together, and hope that's readable. I mean, it's pretty readable. Anyway, this is basically the top module, and that's the name port connections, if you guys have noticed. Notice how we're doing dot clock and then bracket open, bracket close, clock. Yeah.
And you can also see here with the mux declaration that it doesn't specify what the parameter is, so it will default to 16. But if you wanted it to be something different, like a 12-bit mux, then you would do the pound symbol and then put 15 in there.
Yep. So right before the first bracket open, that's right there. You can pass in a 15, or maybe
Or
a
a 12.
4.
I made 12 for a 12-bit mux. I don't know why I said 15.
Well, 15's right. I mean, right now it's 16 bits, so.
Yeah.
Oh yeah, I think I talked about the name port connections in the comments there. Yeah, I guess this one's pretty straightforward. I think a lot of the students have done instantiations before, right?
Yeah, I think I've seen that in the last lab. The people have to use their segment decoder.
So yeah, this is probably a situation that's, yeah, nothing too crazy is happening here.
Yeah. Shifter. Flasher.
I mean, you can name it whatever you want, guys. You don't have to use my convention here.
Yeah. I would have just gone with like Flash F1.
Yeah, that would have been. Yeah, I guess that would have been easier to sort of piece together that it's just a function name rather than a module name rather than the actual module type.
Yeah.
I think you can instantiate it without the names, but you know, Vivado will complain.
You can? But then you wouldn't be able to do more than once, though.
That's the problem, yeah. You can do it once, but you won't be able to get away with it more than once. Because then it'll assume you're trying to call the same module twice, but...
Yeah.
Yeah, I think that's a case where it'd give a lot of errors, but it'll still generate some hardware. And if you have more than one module, it'll silently delete the other one. If it does actually generate a bit stream.
I think that's the next part, like generating the bit stream, actually.
Yep. So if you guys are finished with this and everything looks good, I would recommend running a synthesis and making sure you have no warnings at all, like none.
Yeah, the next step after this is and make sure this is your top module. Like
Yep.
you right click on it. So
Because otherwise you'll generate a bit stream for your behavioral. Oh no, we still have to do the constraints. I forgot about that.
Was that one not filled out?
No, it's not filled out.
Do you have it in the slides, or
Yeah, I have it in the slides. Don't worry.
is it the next one?
It might be after this, right after this. Yeah.
Let me just do a quick check. It says top. Okay, so you do it next. So yeah, has everybody managed to write this down, or are people still going?
Well, it's quite a bit to type out, so I guess we can give it a couple more minutes.
Yeah.
Oh,
I'm still writing, but I took a screenshot, so like it doesn't really matter.
we'll wait. It's no big deal.
Yeah. So how's everybody finding the course so far? Is it too hard? Is it too easy?
Labs are pretty annoying because we haven't been taught the stuff we need to know to do the labs yet sometimes. We still you're in the early lab sections. But other than that, the course seems to be going all right.
Yeah, that's one of the problems is you'll notice there's kind of a disconnect between, well, all the lectures, the theory and all that stuff, and then the actual labs, which you actually apply like right away.
Yeah.
But yeah, over time the lectures will eventually cover the stuff you'll need in the labs. It's just at the beginning there's just a lot of theory to get through. So.
Yeah, this course is hard, but it's quite useful.
Yeah, and Prof. Mason does say it in class, I'm sure he said it in one of the lectures already, that this is one of the few courses you can take and get a job with right away. And yeah, he's not wrong. I mean, this is something that you can apply right away.
Yeah, that's why we're here.
Yes, I think it's a little bit better than just learning a C programming course, right? Because with C, they'll like expect you to actually do more with it, but something like Verilog is so niche that just knowing enough of it will be enough to get you a co-op sometimes.
Yeah, and sometimes they hire people that don't know it yet and are just good at other languages because they're willing to train you on it if you're willing to learn.
What helps is it's very niche, right? I mean, in the sense that it's in demand, but there's not enough students actually learning it.
Yeah.
So
I've actually seen that, like, I remember, like, I got messaged a few times on LinkedIn by recruiters asking about my Verilog experience.
Yeah. I think once I got one of those, recruiter in-mails for some position that they wanted some guy with 10 years experience for, and I'm like, did they even open my profile?
They probably just, like, searched Verilog on LinkedIn and then, like, mass emailed
it. Yeah. That seems to be what some recruiters do, so.
Yeah. So yeah, the amount of jobs in this field, there's more of them than people that can actually do them. So if you choose to go into it, you will definitely find work, and it's also pretty lucrative and fun if you're into that.
Yeah, on average, this tends to pay more than software engineering. So, base software engineering, this can pay more in the long run, maybe. But it depends on the company, of course. Like,
yeah.
You have your crazy startups and unicorns, that'll pay crazy amounts for software, right? But
Shopify,
yeah. But I can tell you that this field can pay just as much as Shopify can after graduation. Maybe not right away. Maybe not for co-ops. I think Shopify pays their co-ops quite a lot, but.
My roommate worked at Shopify, and he earned like a $70K salary.
But that's as an intern, right?
Yeah, that's as an intern.
Yeah, that's pretty good. But as a new grad, you'll make more as doing RTL. You will make a lot more than that.
For like a digital work, it's like minimum 6 figures.
Yeah, I've like right after school, if you've got some co-op experience, you can make 98 to 100 and something K pretty easily.
Yeah.
So yeah, this isn't this stuff is valuable.
Yeah. Yeah, actually, at the end of the workshop, I have like a small part where I talk about like what actually happens in the industry and some useful stuff to know if you are interested in going into this. So has everyone had a chance to write it down, or?
Oh, he's getting red lines under each call line. Okay, could you hover over it and kind of tell me what it says?
Are you talking to Anush?
Yes, he's DMing me.
Error, syntax error near the curly bracket. Clock divider is an unknown.
There are no curly brackets in this file.
Gabriel.
I think that's what happened, right? It's They're just normal brackets.
Okay.
Yeah.
Gabriel.
Yeah, Hamas?
In the clock divider function, you said dot clock is equals to clock. Dot clock doesn't exist in the clock
I think
the clock
it's
module.
clock 5.
It's it is clock 5 megahertz.
You're
That's the
right. You're right. That is a typo. I don't know why I haven't fixed that yet. I'll fix that. Yes, that's actually supposed to be clock 5 megahertz. Sorry, guys. But just a dot part. Just a dot part, okay?
Yeah, right here.
So you still want your input to be clock, but you want the right after the dot to be clock 5 megahertz.
So yeah, the dot signifies which input you're trying to target with the assignment.
Sorry about that, guys. Hope it didn't. Yeah, this was a situation where I think my clock divider was a bit different somehow, and I didn't get an error, so. Yeah, I think that's another thing that's important to point out is be very careful with your variable names, really stick to them. Things like this can happen easily.
Where do we put clock 5 hertz?
Oh, right here.
So,
you see my arrow?
Oh, they can't see your mouse.
I can't see the arrow.
So dot clock. So you see where we have dot clock, we want to replace that dot clock with dot clock 5 megahertz.
So everywhere there's dot clock for each one of them?
No, just for the clock divider.
So yeah, the very first dot clock.
I should have left the line numbers, it would have kind of helped.
So one other question, if we're able to run synthesis and nothing like red shows up, then it's good?
Check your messages, and if nothing is there, then yeah, generate a bit stream. It's all good to go. Wait.
I think we still have the
constraints. My bad.
The constraints to go.
You're good so far. We just have
Okay.
one left. So.
All right. I guess we can move on to the constraints now.
Yeah, so just make sure everyone's fixed their syntax issues. Okay, I think everyone should be good by now, right?
I have another question. I think since we made the mux, the switch for the mux dot cell, we made that a 3-bit, I think, or a 2-bit. I can't remember. It's not a 1-bit, anyways. Do we need to define the func dot cell? Oh, okay, I see you did that. My bad.
Yep.
So we change under clock divider to dot CLK underscore 5 underscore HZ.
Yes, so you can copy that exact name from your clock divider module. You don't have to type it all out. You just copy it.
Oh,
I mean,
okay.
copying also prevents you from making typos. I typically do that as well. So if there's a typo in my main module, it's going to be in all my top modules. Yep. Yeah. Is that it? Like it was 5 megahertz, wasn't it?
Yeah, it is 5 megahertz.
Yeah.
So is it?
Yeah.
Is there like an M?
Yeah, there's an M.
Let's go back and
I got it. There we go. Wait, let me make sure. I'll check the actual. Yeah. So it was that. Wait, I just sent that to Anuj. My bad.
Yep, I don't have any more syntax errors.
All right. So then we're going to move on to the constraints, and then we're actually going to get this on our board. So.
All right. So make sure you set it as your top module. And now it's time to set up our constraints.
I changed the name. Nice.
So you just you double click on the file and then you should have it open up on your screen.
This is where we're setting the clock to 5 megahertz instead of 100 hertz. So right now, I think by default, you're looking at 100 megahertz clocks. We want our period to be 200, and we want our waveform to be half of that number. So, you know, this is like F equals 1 over W, I think. 1 over omega, was it? Yeah. So you kind of assign the frequency based on your omega value. So, and I think the 200 is in nanoseconds. It's not in seconds. So
yeah, that's like the minimum frequency you can go to straight out of the FPGA before you need to start using dividers.
yeah, if you try to go below that, it'll cap out at like 4.87. I think someone is generating some background noise. Okay. Yeah.
Where did you get the constraint file from? Or is it just the one we've been using?
It's the one that I posted earlier. I guess I'll post it again. I'll give everyone a link and I'll explain how to grab it. Yeah.
I think it's just because I joined a little late, so I don't have a memory of the Zoom chat.
Okay.
Yeah.
All right, thank you.
So once you open that link, you're going to want to right click on somewhere on the web page and then just say save link as, and you'll be able to save it as an XDC file. Make sure that's in your constraints folder.
A quick question: how do you guys decide the period and the waveform number? Like,
So the waveform number is always half of the period, and the period is in nanoseconds. So 1 over 200 nanoseconds will give you 5 megahertz.
What about the waveform? Like, how would you decide if it goes from 0 to 100? Like,
It's just half of 200. So 0. If the period was 100, it would be 0 to 50. So yeah, you always want to assign that to 0 to half of the period. So it follows a very similar format.
Okay.
I think the idea would be that it's like.
Is that like the duty cycle?
I think so. I don't know. I honestly don't really know what it is, but I just know that you got to set it to half. But all we really care about is the period, I guess. That's the more important value we need to set. But the waveform, you got to set it as well, because otherwise it'll complain.
Yeah, we're also using the clock edges, so pause edge, meg edge.
Yeah.
So the actual duty cycle isn't as important. As long as it's like half, that's good enough.
I think if it's anything besides half, it'll complain. Like you won't get a synthesis error, you'll get something in implementation and bitstream generation. It'll just say something weird. I think everyone's good to go now, right? Let's go to the next part where we're messing with the other constraints file parts.
All right.
So I really wish I put the LEDs as all caps. I apologize, but you're going to have to go through that and make them all lowercase.
You can also just Control-C the lowercase LEDs and then double-click on the large case and hit Control-V.
Yep.
And it'll automatically replace them.
Or we start a Python workshop and show you how to find replace with Python.
You can also do that with Vim.
Oh yeah, that's true. Can you run Vim on a PC? Windows? I think you can.
Yeah, yeah, I do it.
Why would you do that to yourself?
Why not?
Don't get me wrong, Vim's great on the terminal, but I guess you got to keep your skills sharp, otherwise you kind of forget the shortcuts. So
I have like a Ubuntu kind of software on my Windows PC, so it can open up like directories as though it were like a Linux terminal.
you're using something like PowerShell.
Kind of. It's like
Yeah.
Git for Windows, sort of.
Ah, yeah, I know what you're talking about. Yeah, it's a little annoying, but Windows has different commands, right?
Yeah, and they're all like legacy stuff from DOSBox. Or
Windows for Windows backwards compatibility is very important.
Yeah.
That's why you actually still can't name a file or folder com.
Yep.
All uppercase com won't let you.
Yeah, but the good thing is if you made like a file 30 years ago, you can still open it today.
Yeah, that is pretty neat. But I mean, if you stop and think about it, that's kind of useless now. You can always just spin up a,
Not for the government. They they have trouble changing anything at times.
Okay, yeah, that's another story.
So did everybody manage to replace this long sequence of LEDs?
It's a lot of fun, eh, guys?
All right. I guess we can keep going now.
Yeah.
All right.
This part's a little quicker. We're basically going to where the PMOD switches JD are, and we want to also mess with JC. These are your virtual switches and your virtual buttons. So our function select is 2 bits, so we have to assign those individually to each switch. And then we got shift select, which is the 3rd. And then we got a reset button,
Which is tied to a BT and U, which you might have noticed on the GUI for your Vivado FPGA.
The GUI actually works pretty good. I was
Yeah.
surprised. It's like it just works.
Do you know what they wrote it in?
Arduino, right? It must have been Arduino. Oh, the GUI's Java. The GUI's Java, but the
Oh, I had a feeling it was Java.
it was Java, yeah. It's like the chess program.
Yeah, I've made too many games in Java not to like recognize it.
Yeah, it was definitely Java. I would have done Python personally, or maybe even a C executable, but
Yeah, Java has like a scene builder.
T would have been ideal, I think. C and Qt, that would have been good, but it would have been hard to program. I can see why they went with Java. Like all the libraries are already there, so it was pretty easy to put together.
Mm-hmm.
Yeah. All right. That's 4 lines, guys. I think we can. All right. Yeah, we can move on. All right. Now we can run the synthesis to see if we got any errors. You shouldn't get any errors at all, or any warnings or critical warnings.
If you do, let us know.
Let us know. Yes. You have to comment out the ones you don't use. I guess I should mention that. If you're not using any of the values that are uncommented, comment them out with the pound sign.
Yeah, there's also like you can just go over and highlight and then right click, and there should be like a tab that tells you to comment everything. That's
hashtag
highlighted.
port I don't want to use. Okay.
Sorry, do you mind going back to the last slide? I just want to make sure that reset was on the PMOD header buttons JC. We haven't used that before in class. Okay, awesome. Thank you.
All right. I think we're So once you got all that, make sure you save everyone. Control S all the modules. If you have an asterisk above the module, you know that you haven't saved. So
If you run the synthesis though, doesn't it automatically save or ask you to?
sometimes it does. Depends on if you clicked "Don't show me this again" by accident.
Oh. Yeah.
I think I messed up my my Vivado instance by doing all kinds of, because I was annoyed by these pop-ups and I kept pressing that button, so I messed things up. So every time I ran a synthesis, it would open up an implemented design. I was like, I don't want this anymore.
Oh boy.
And it would automatically go through this whole implementation process that I don't want, when I really just wanted to generate a bit stream at the end. But it can happen. Just don't ever press the don't show again checkbox, guys.
Yeah, so after your synthesis is finished, you can hit run implementation.
Provided you have no warnings or violations or anything like that.
Yeah.
Bitstream process will generate 2 warnings, but both of them don't matter. Something about VCO, I don't know. I don't know how to get rid of them, but they don't really matter, so you can ignore them.
As long as it's like a warning, a non-error, it's usually okay.
If you get an error at bitstream generation, but nothing in synthesis and implementation, that means something is wrong with your constraints file, more than likely. So that's an important tip to remember if you're experiencing some issues. And unfortunately, the bitstream errors are a lot less descriptive than the synthesis errors. So you're going to have to actually look at it and try to figure out why it went wrong.
So is anyone's bitstream still generating? Actually, wait, Gabe. I think you have a funny slide on this. I think.
Oh yeah. Open that.
Yep. Program. Press the generate bitstream.
Yeah. You should have kept this on.
Yep. Now you just wait 5 minutes.
The Microblaze workshop, I replaced the 5 minutes with 30.
Does it take that long?
It's 30 minutes.
To compile?
Yeah, it's pretty bad.
I remember that.
We basically had to have like a mandatory lunch break.
It took like over 6 hours. Like let's call that.
That workshop was great, but no, just having to wait that long for generation.
I hope you guys ordered pizza.
No, we just went to Pizza, I think.
You should have.
It would have been nice to order some pizza for that one, because those who stuck around for that workshop really deserved something.
Yeah.
Yeah.
Honestly, we should have. It wasn't our academics budget.
Yeah. Well, next time, I guess, we can get virtual pizza.
Not sure if I can like send people pizza.
Looks like mine failed. Is that because I'm not connected? Like I'm not on the actual lab itself?
Well, no, that shouldn't cause an issue in the bitstream generation. It still should generate a bitstream. So what is your messages? Can you look at them?
Yeah. Let's see. So it says unspecified I/O standard.
That
121 logic ports used I/O standards.
All right. So
say,
look at the very end. There's like of that message. It should say problem ports, and you can look at which ports are causing the problems. Odds are you may have forgotten to comment out the ports we're not using.
Yeah, let me double check that.
Should be at the very end of the red box that got generated.
Yeah, I really didn't like that violation. It took me a long time to figure out how to read it, because your actual problem is at the very end of the.
Yeah, I didn't realize it at first when I was reading it. I'm like, well, this isn't helpful.
You really should just put the problem ports at the very beginning. I think it's more important than the code name of that port.
Yeah.
You be able to go back to some of the first modules, because I joined late, so I didn't have a chance to write them down.
Which ones were they? Like the logic gates?
I think I have the I think I have the mux, the randomizer, the top module, and the constraints, but anything before that.
The clock divider.
Yeah.
I'm
that
probably
too.
missing the clock divider.
You have the flash.
I don't have the flash.
All right, take a screenshot of that one, and let us know when you have it, and save it somewhere. Then we're going to go and get a screenshot of the clock divider. Then I think we'll be okay.
I have the screenshot of the flash module.
Okay, let's show them the clock divider. Yeah. So you want these two modules set up, and you want to make sure that you're saving them outside of the project. Kind of went over that, but if it's not a big deal. We'll you can just go over the slides and follow the steps for next time.
Okay. I don't think I am saving them outside of it because I've just been clicking new source. So.
Okay, yeah. It's a little annoying when you do that. Like, I mean, just to extract the files later if you want to pull them out, but
yeah,
it'll still work. That won't be an issue.
How would you create a new source without it being inside the folders?
So there's an option there where it says instead of the default, you can select choose location.
Okay. All right. And okay, so let me just make sure I have everything. I have the constraints. I have the flash module. I have the top module. I have the randomizer. I have the shift.
Sounds like everything.
But I need to find it. I have a lot of screenshots on my desktop of random things, so.
Oh. Did you manage to get one of the clock divider?
Yeah, I got one of the clock divider.
Okay, so I think that's everything he needs from there.
Yeah.
Yeah, so is there anything, well, maybe show him that list, see if there's missing anything. Don't worry about the example files. We don't need that for the final design, but.
Okay. I thought I had a screenshot of the mux, but I can't seem to find it.
Oh, we can show you the mux. Yeah, no big deal.
Oh, there it is.
All right. We'll try to type all these ones I haven't done yet very fast, but might take me a minute. But thank you.
Yeah, don't worry about the comments. Just write out the code.
Yeah.
Okay,
Yeah,
so I think somebody here should have a bitstream finished. At least one.
Did anyone successfully generate a bitstream?
I guess not.
In the error message, you said that it will list out the ports that are causing issues. Where would that be at the bottom? But
it'd be at the very bottom of the message, at like the very last line. It would say problem ports, this, and that.
that doesn't show up for me.
What about?
Sorry, go ahead.
It says errors found during DRC.
Is that a violation or a warning?
Yeah, that should Oh wait, yeah. Is it in red or is it like a different color?
It's like a red exclamation mark error.
Okay. Share your screen. Can everyone share their screens or?
Okay, I gotta log into Zoom on my computer.
For a second.
Or wait, maybe send a.
I'll send a screenshot.
Send a screenshot to me somehow.
Okay.
The messages.
I have like a similar error to Anuj, and like I found the like the problem ports like part. I can send my screenshot in too, like if you want to compare them.
Sure. Yeah. I think you can send it on Zoom, right?
Yeah.
Is it okay if I can send it to you through Discord?
Sure. Yeah, that could work.
Yeah, I think I'm missing something in the constraint file. I think these two haven't been defined. But yeah, if you guys wouldn't mind going back to the slide with the constraints, I can see what I missed. It says I'm missing clock and shift_cell.
Oh, Shift
Yeah.
L is in switch 2.
Awesome.
Oh yeah, I see.
Yeah, I just copied them all as func cell.
Oh, clock 5 megahertz is defined as that.
Wait, was our top module clock 5 megahertz or?
We had a here. It's listed as the input being clock, which that should be clock 5 megahertz.
Yeah. So what does the constraint say?
Clock 5 megahertz.
Okay. Yeah. Okay. So just replace that clock 5 megahertz with just clock there. Sorry about that, guys.
No worries. Thank you.
Yeah.
Sorry, replace it where?
So you see clock 5 megahertz in the constraints. We want that to actually just be clock.
Okay.
I think that's same, like that's the same issues, and yeah, that's Anuja's only problem, by the way, I think.
Oh, nice.
Okay, so
So then-
that's yeah.
Where's the clock 5 megahertz in the top file?
Like technically, you only have to
no,
change
no.
in the
We
constraints.
we don't have to change the name of clock 5 megahertz in the anywhere else besides here.
So if you like
Mistakes in the top file.
if you see the circled value on screen right now, so just change that to the same clock as the top module input.
All right.
A quick question. So let's say that if there was an error in the bitstream, but like let's say the synthesis and implementation works, and we fix the constraint file, do we have to re-synthesize it and re-implementation, or do we have to go back? Or can we just?
You gotta redo everything, unfortunately. I think, yeah. Or maybe you could try generating a bitstream again, but it'll say it's stale because you've changed the source file.
Yeah, that's what happens for me.
Yeah, you have to re-implement it because like it has to redo the mapping on the FPGA.
Oh.
And if you change any of the source files, it'll say it's stale, so you have to redo it. It's a little annoying, but yeah. This is why problems with the constraints file tend to be the most annoying to deal with, because they don't pop up in synthesis and they only pop up at the end, and
You have to go through the whole process.
So in this constraints file, like on line 7 and 8, are we defining a clock or are we passing a clock in? I'm kind of confused about that.
So that set property is actually the clock that's already in the FPGA, and we're just changing that one to be specific. We're creating a clock, but
Like we're setting the parameters for the clock?
yep.
Okay.
So
I was wondering because like the clock, like CLK is an input for top. So I was wondering like did we get it from here or okay, that makes sense. If we
so
get
it's coming from the constraints file. That'd be a good way to think about it. Like imagine like it's a switch that's toggling very quickly, but we got to tell that switch how to toggle.
okay.
And yeah, we can't build one in Verilog, so it has to come from the FPGA.
For sure. Oh yeah, so I managed to generate my bitstream correctly. That's good.
No warnings, no nothing.
No.
Awesome.
All right. So if you're on the lab computer, you can probably try programming.
Yeah. Let's see.
All right. I think we waited a bit more than 5 minutes. Just change that to like 20 or 15.
Guys, don't worry. We're almost done. This is almost over.
So
Yeah,
mine
we're
also
close.
completed.
Hey. Nice.
Nice. Right. If no one else has any issues, I guess we can keep going.
Like same here.
All right, that is perfect. So now that you've done that, if you're on the lab computers, you can do the Open Hardware Manager. And then you can open target and start programming it, and then open up the GUI and start doing stuff with it.
Oh, this is where we're talking about the TCL script, so we'll get to that in a bit.
This looks really cool. It's just like going like from left to right, right?
Is that what it's doing?
Yeah.
Press the first switches.
Okay.
There's one.
Yeah, now it's just blinking. Like all of them are blinking. And then
All right, set two switches on and one off. Was it? Oh no, just keep messing with the switches until you see the random generator.
Yeah, I'm definitely seeing like with all sorts of patterns. Pretty cool. Let's figure out which one is the random generator.
So I think 0 should be the flasher.
Yeah, I think 0 is the flasher as well. I think
1 is the shifter, and then 3 is the well not 3 but 2 would be the randomizer.
So when all switches are off, it goes from like the switches just go from like left to right, and when switch 2 is on, it goes from right to left. It just like reverses the order that like the switches like turn on.
Oh yeah. There's a third switch, and that controls the direction. But the third switch is ignored in the other modules.
Okay.
Are you
So
able to
it's
see
like,
the randomizer yet?
No. Wait, I think it might be the off button. No.
I think you have like everything off, but only one, like switch 1 on.
Yeah, switch 1 has to be on, I think, and that's it.
Yeah, I think switch 1 might be it because
It's spitting out some random sequence, right?
Yeah, it's spinning out random sequences.
Okay,
Mhm.
perfect.
That's it.
So originally I made that so that all the bits were random and it wasn't like shifting, but that required a lot of typing out. So because you have to basically make that same module for each of the bits. So you're just copy pasting a bunch of lines.
Jeez.
But yeah, I mean, you can apply that and do that if you'd like, but it's kind of a process.
Mm-hmm.
Because what we're generating is we're generating 1 random bit per clock cycle. We're not generating more than that. Okay, how's everyone else doing?
Can you repeat what's supposed to happen when each switch is like switched?
Oh, nothing. It's supposed to just blank, right?
At
I mean,
0,
like each individual one. So like for switch 0, what happens? For switch 1, what happens?
So if nothing is on, it should be flashing, I think, right?
Yeah, that's what's happening. Yeah.
So when you turn on the first switch, it starts shifting. Oh yeah, that's perfect.
Yeah.
That explains how it works. Yeah. So
So-
if both switches are on, nothing's going to happen. That's the rule. Function select. If function select is 3, the output is 0.
Oh, I see. Okay.
I'm not sure if you talked about this already, but do we have to do anything with the time scale that like gets automatically generated if we?
Nope.
create
It's
user?
always 1 nanosecond. I think it should always be 1 nanosecond. I think it's a good.
Yeah.
Okay.
Our silicon isn't good enough to be in the picosecond range, I think. So
All right.
Not yet.
not on FPGAs, that's for sure.
Maybe later.
But in ASIC
Sounds
world,
good.
everything is picoseconds and femtoseconds, and it's fine. But not with FPGAs, no. Yeah, I don't think any of the FPGAs are in the beyond nanoseconds right now.
Yeah.
Like even the most expensive ones are still on the nanosecond time scale.
I think the only part that's actually in picoseconds is like transition time.
Yeah.
Whereas like the actual like clock, the whole clock cycle is usually always defined in nanoseconds.
Yeah, one thing that's kind of interesting to note is FPGAs, the more money you spend, you don't really get a faster FPGA, you just get more space.
Yeah.
That's essentially what you're paying for.
So who here is still working on their bitstream?
I'm still writing out code, so like, don't worry about me. But yeah.
All right. So I guess we can keep going and show off the TCL part.
All right, so if everyone has everything up and running and we're good to move on, then yeah, the TCL part is kind of interesting. Yeah, so here I'm basically talking about, if you wanted to put this on GitHub, for instance, you don't want to put all that junk on GitHub. There's a lot of junk in this project folder. Ideally, you just want to delete this thing and never have to open it again, but not always. It's not the way Vivado wants it to be. It wants you to have your files in there for some weird reason. But yeah, so next slide. If you actually upload your project folder to GitHub, this is actually what you're going to see. You're going to see like 48% of the thing is system Verilog, which you didn't type any. And then like 20% is shell, and you didn't type any shell for sure, right? 16.2% is Verilog, so that could be our stuff, right? But then you got all this other stuff like JavaScript and HTML, and there's a lot of junk in these folders, and you just don't want to have to move those around all the time because sometimes you just don't care about stuff, right? And in the final labs, like if you're doing your egg timer, it can easily reach 300 megabytes of space. You can't send that to your partner, right? I mean, it's very difficult to have to email him a 300 megabyte file. You'd have to put this on a Google Drive, and it's just a lot of stuff there that you don't need. So next slide. So yeah, the solution is to use TCL to sort of automate all this stuff for you. It's a scripting language within Vivado that you can use to sort of do stuff like create my project. Okay, do this, do this, do this, do that. And if you have your directory set up correctly from the beginning, you can write a TCL script that'll automatically build your entire project folder without having to go through the wizard, without having to add sources, point out where they are. So I'll kind of show you how that works. Let's go to the next slide. So you want to write a project TCL, but you want to make sure you do not import the sources. So we'll keep this slide open for a bit. And you basically want to select the build TCL file to be right next to your source files. The thing, the way the TCL script works is it'll go relative to where the TCL file is saved. So it has to be nearby.
So yeah, just to recap, you go to File and hit Write Project TCL when the menu pops up. And then you select to build to the directory that you made at the very start. And you make sure you don't import your sources.
Yep, make sure you do not import sources. You don't want to ever do that. It's a really silly thing to do, and can really ruin everything.
This is like, if no one's having any issues, we can also move on to the next step.
So once you generate your TCL script, you can kind of look in there and see what it's doing. It's basically importing directly from your HDL folder. You'll have your randomizer.v, your flash.v, and it'll automatically import and start using them. So if you actually wanted to run this script, I think the next slide I kind of show how to run it.
So yeah, this is like the actual contents of the TCL script.
Yep. It's an ugly language, so try to avoid having to work with it. But you basically want to type in cd, the directory where your TCL script is. And then you want to do a source build.tcl. So cd basically tells Vivado, take me to this directory. Before running that command, though, make sure that your project folder isn't there. Maybe move your project folder somewhere else, maybe outside, because it'll try to overwrite it, and it'll have issues doing that.
So this is to like rebuild your project in a different directory, basically.
Yep. As long as the source files are right next to it, it'll rebuild it. So the idea here is that you do this every time. You make the project folder, then you can delete it, and then you can save your files, send it to your partner if you have to, and then your
TCL.
partner can build it.
This looks like Linux commands though, so I believe
It's a little weird. It's like Unix. CentOS. It's like CentOS. The source command is not. Well, I guess not really. You have that in Ubuntu. Although that does work on Windows if you're worried about that. The only problem is the CD doesn't autocomplete, so you got to actually have an absolute path. Type it out completely.
So the tab completion doesn't work?
Yeah, and also backslashes. If you copy from Windows, it's going to have backslashes. And it's going to ignore back. Really stupid, but okay.
That's only if you're working in Windows.
Yep. I don't think anyone here is working on Ubuntu, though.
I think Macs. Do Macs use the forward slashes or backslashes?
Macs? Oh, Mac. Okay. No, they use forward slashes like Linux does. I think Windows is the only one that uses backslashes for some reason.
Yeah. All right. We can move on now.
Yeah, so if you run the script source build.tcl, yeah, you'll rebuild your whole project. So this isn't really an important step. I mean, this is just mainly if you want to use this workflow in your future labs to clean things up a bit. It can clean up a lot if you don't have a project folder you got to share with your partner all the time. But yeah, I guess we can move on. Yeah. All right, Constantine.
All right. So this is kind of like we have come to the end of the workshop, and now this is the point where I sort of discuss like the what happens in the actual industry and what's relevant to know. So when it comes to actual industry work, the main choices that you'll likely be working with are either System Verilog or VHDL. System Verilog is the object-oriented extension of Verilog that is primarily used to construct the test benches that enable the testing of designs. While the designs themselves are written in like Verilog components. As you can see on the right side here, this is a class that's written in System Verilog. So currently, it seems to be used to describe sort of like a stack that's used to store things. That's likely used for testing to simulate a stack that's being done like circuit-wise with Verilog. And here's kind of like a diagram of what's changed so far. So currently, you'll mainly be using Verilog 1995 stuff for your labs. So that's where you have like your wires, your wedges, your integers, your initial statements, and all that other stuff.
You actually are using a bit of 2001 too, though. I think we've got. Yeah. I think we have some stuff from 2001, like the power operator.
Yeah, that is
today.
Yeah, so the vast majority is from what was initially done in 1995, though. Whereas nothing you're currently using is from System Verilog.
I did not realize System Verilog had so much stuff.
Yeah, it's like it basically adds the entire C language to it, plus some more stuff.
Yikes! Void casting union structures. It sounds painful.
Yeah.
But it kind of makes sense. I mean, most C developers would kind of see would know how to apply this stuff pretty quickly.
Yeah, but like career-wise, you'll you'll see like kind of like two streams to go off of. You'll either be like a designer or a verifier. So the verifier is like tasked with knowing system Verilog, and they'll be responsible for test benches and the like, and testing the designs. So essentially what they have to do is kind of like create sort of like an abstract of the circuit with system Verilog using the object-oriented components, because it's a lot easier to do that than with just regular Verilog code. And then they'll like compare sort of like the outputs and inputs that are driven through both the Verilog version and the system Verilog version, while also like the system Verilog component will also be generating the inputs themselves that are tested. And then there's also like the designer stream, whereas you'll mainly be working with like the original Verilog that you're currently doing. So that's why, despite like what you're doing being quite old from like the 2000s, it's still quite relevant to actually know it, because it's still very valuable to the current job market.
Oh, I absolutely agree.
Yep. And here's just an overview of like if you go the verifier route, you'll be working with this this methodology called UVM, which is known as Universal Verification Methodology. And on the left here, we have like a sort of like an abstract overview of what kind of code you'll be writing. So you'll have like one big class called a test bench, which will be kind of like your top module, and you'll like create other things like your tests, your environment, and like your agents, your sequencer, and your scoreboard. And within your test bench, you'll instantiate the tests as well as the design under test, which is the Verilog code that the designer wrote. And then your stuff like your sequences will be stuff that you write that determines what inputs will be driven in. And the goal of these test benches are to drive the complex inputs to test the devices, verify that the output and behavior of the device under test is correct, and to monitor the coverage of cases, so to ensure that every single possibility within reason has been covered. So it's stuff like if has every bit been set to like 1 or 0, or like every register transition combination has been achieved. It doesn't necessarily have to be every single one. You can waive certain cases if they're deemed non-relevant. And actually also just like a fun thing to know, for these kinds of things, the things that take like an equal amount of work to create is the design under test, the scoreboard, and the rest of the environment. It's because the scoreboard basically has to simulate the actual design under test in system Verilog, so those can take, or can be like thousands of lines potentially, which can be much longer than the actual device, depending on the situation.
Yeah, sometimes the test benches are much larger than the RTL that they're verifying.
Yeah. I remember like I worked on the environment back at my old internship, and it was like well over like 2,000 lines of code for a 1,000-line device. So yeah, it was pretty crazy, but it was really interesting work. I would recommend people going into it.
Yeah, you got to start off in verification if you want to end up in design, but I think some people can end up in design early on. Depends, but usually people who are in design have had a few years of verification.
Yeah, like I just got like a new internship where I used my year of verification experience to leverage the design part. So I managed to get my foot in the door in that, which is good. So you guys will likely end up doing the same thing if you decide to go in this field, though I've heard of some jobs that will start you off in design if they really badly need designers working at their company.
Well, especially in FPGA development, where rapid prototyping is a thing and verification isn't as important. In the world of FPGAs, you can always just send a new bit stream to your customers if something is wrong. But in the world of ASIC, where things are actually printed, if something is wrong, you got to do a recall and you lose millions of dollars because you got to refabricate everything.
Yeah, even with a ASIC, which is application-specific integrated circuits, so stuff like processors, there is an FPGA step after all this UVM stuff is done. So they'll take the DUT and put it on an FPGA and then test it again that way, just to ensure that it works physically. So they have like a lot of steps, because once you print the chip, you can't recall it, because you spent like millions of dollars already to manufacture it. So
Yeah,
that's
it's a
why
serious problem when that happens. And usually, I think Ralph Mason has mentioned this in his lectures. When something like that happens, whole teams get fired.
Yep.
It's serious.
They end up doing the Nortel salute. Have you heard of that?
Is that the salute when it finally shut down,
Yeah.
or
It's where you point your fingers at each other because something went horribly wrong. You don't want to take the blame. Yeah, that's all for now, though. Thanks for coming, guys. You now have a pretty cool design to show off and to help you on your future labs.
Yep, definitely. You'll definitely be able to use the clock divider. That's going to be pretty helpful. All the other modules, you'll definitely be able to apply to your final project. I think the randomizer would be kind of interesting to see how people would use that.
Yeah, or the multiplier, if you guys choose to do that.
Yeah, there'd be some interesting applications I can kind of see being put together. Like, you can make a bad music generator with a bunch of randomizers.
You can make a dubstep generator.
It would just be this like really terrible, like just a collection of bad tones that are just constantly being played.
Yeah, it'd be a good alarm though.
Be a good alarm.
Will this PowerPoint be posted anywhere? Or
We're gonna try and post this on Facebook, and
I'll post a link in the Teams chat as well to it.
okay. All
so
right.
I think we just need to polish up a few things, like the clock thing. We'll need to sort of go back and fix that. But
there's a few typos though we really should take care of.
Yeah.
So once that's
Thank
done,
you.
I mean, we might have that ready to post by the end of today.
Okay. Thank you guys for doing this. I appreciate it a lot.
Yep, no worries.
Yeah, thanks so much.
I hope you all learned something.
Thank you. This was really helpful.
Definitely learned something. This is really interesting.
Yeah.
And maybe you guys will be interested in a career in this stuff.
I knew I was as soon as I took this course. I almost dropped out to do software engineering, and then I took this course, and I was like, whoa.
Yeah.
I like this. This is exactly what I want to do.
Yeah, this course made me not regret choosing electrical.
Yep. Same with me.
There's a reason why Keiko has a title for FPGA, like FPGA God in IEEE.
Well, I definitely love this stuff more than analog. I'll say that.
Yeah.
Analog courses haven't stuck with me, but everything digital has. Like, it's been very enjoyable for me anyway. And even if you want to go the analog route, you can definitely go analog with a bit of digital. So
Doesn't it have VLSI?
yeah, there's a lot of analog modeling that you'll have to do in circuits, right? Some circuits are actually analog components, but you need to model it so that you can connect it to your Verilog and see what would happen.
Technically, digital doesn't exist. It's just a very controlled analog. Because even with the digital circuits, you have to like analyze things like parasitic capacitance, which can affect your clocks and rise and fall times.
If you do get into that, yeah, it's also a pretty interesting field. Like you mostly do R&D mostly, but
yeah, you want to make sure you don't accidentally build like an oscillator.
or yeah, just make sure actual data is being passed and not disappearing because of
Nice.
parasitic behavior.
Yeah.
But yeah, I guess that's everything. Anyone have any questions?
I have one last one actually. When you're trying to run the TCL file, like what exactly do you type into like the command prompt?
Source build.tcl, or we can go back to that slide.
Yeah.
Yep. At the very bottom here.
So you want to make sure that you do cd, the actual directory where the TCL file is,
Mhm.
and then do a source build.tcl.
Like source and then space build and then the TCL file?
Yep, so build.tcl is the name of our TCL file.
Okay, I named mine something different.
Okay, so source, whatever your file name is. That would work.
Yeah, when I do that, it says source isn't recognized as an internal or external command. Operable program or batch file. I don't know what that's about.
That might be that it doesn't see it. It doesn't see the actual.
You might not be in the right directory for it.
You want to make sure that the build file is in the directory that you CD'd into earlier.
So like,
Otherwise, it's looking for something that doesn't exist.
The build
like
file is the TCL file, right?
Hmm?
Is the build file the TCL file, or is it something else?
The one that we generated is
Yeah.
the TCL file, yeah.
the default name for the TCL file is build.tcl.
Oh, okay.
So if you've named it something else, you're going to need to source that. new name.
Yeah.
So source whatever you named it .tcl.
I am trying to do that, but I think I'm doing something dumb on my end, so I'll figure that out. Thank you.
Did you CD to the correct directory before that, though?
Yeah, I just went to like the like I just typed CMD at like the top of like the file explorer window thingy. So I should be in the right one.
Wait, did you say CMD?
Yeah. Like if you just type CMD at the top of like the file explorer like window that you're in, like it'll take you to the directory that you have open.
Oh, what happened is maybe it's replaced the forward slashes with backslashes.
Maybe.
Maybe.
You want to make sure you're using forward slashes, not backslashes.
Oh, okay. It's fine. I'll look at it later. Thank you.
Anything else?
Could you explain what the pmod switch is? Just wondering, or pmod headers?
Sure. So can we go to that slide where we're the screenshot of the actual thing, of the actual like remote system?
Wait, that's at the very beginning.
Yeah, but it'd be a good way to kind of explain.
Gotta go fast.
Did you not exit it?
Right.
There we go. So if you look close there, the top, like where the Arduino is hooked up.
Yeah.
You know where that is? Yeah. So
On the left side.
So on the left side, we got that Arduino hooked up, and it's connected to header pins JC and JD. So JC is the top one, JD is the bottom one.
Oh, okay.
So that's how they've connected it. The reason they've done that is because there's, those are the only IOs on the board. So.
Oh, okay. Yeah. Okay, that makes sense.
So if we wanted to connect actual pins, they would have had to maybe, if they wanted to keep the same constraints file, they would have to solder cables to the switch points. They'd have to basically mess up the board in order to do that.
Yeah.
A bit extreme, I think. So this was probably the better solution.
Okay.
And not to mention the manual work involved in having to do that. But it is doable. They could have kept the same constraints file if they went there and soldered the Arduino to the FPGA.
Okay. And what happens if what do you call, like in this case, you put like reset into the pmod header? What happens if you don't have, if like a normal master, the normal master constraint file, where would the reset pin go?
Onto a button. So it'd be the same thing. It doesn't change functionality.
Yeah,
Oh,
there
okay.
should still be a one of the buttons labeled.
We're not resetting the whole FPGA. We're just resetting our design. So CPU
Okay.
reset, we can't access that pin because that's actually on the board. We can't
Mhm.
control the CPU reset. But
Yeah, the reset that we have should be really called soft reset.
yeah,
And like
Yeah,
turning
totally.
the FPGA on and off is a hard reset.
Oh, I see.
but yeah, typically in your Verilog designs, you still want to name it reset. I don't know,
Yeah.
but it's not really a reset. I originally had an actual, like, the design used to be different. It used to have a CPU reset pin, like another button.
So that would be like
That
your hard
would-
reset.
Yeah, that would be the hard reset. But I ended up removing that because it was just, it overcomplicated things.
Okay.
So, anything else, guys? Or I think we've been what, exactly 3 hours?
Exactly.
Yep.
Yeah.
Not bad. Not bad.
Was that the same as last time?
No.
No, like
It's
the
4
last
hours.
time, 4 hours more.
Oh god.
Microblaze was 5. I think.
Micro was 5 to 6. Like I know that.
It was the whole day.
But like the last Verilog workshop, what happened was that like it was delayed. It was start delayed just because we lost the projector.
Yeah, I told Constantine about that story.
That how CSOC stole it.
Yeah, so I guess we started a bit late on that one. So
Yeah, but like still but still like there was so many people showed up compared to like how much space we had in the room.
yeah, I think people were fighting for space.
It was
The whole
like,
lab was full. It's a terrible time to be in the lab when the lab is full because all the computers generating bit streams at the same time. The
Yeah.
temperature goes up to like 40 degrees. It's just a
Yeah,
hot
I remember
box.
that. I remember that room just being, just the temperature outside and inside is so different that you can feel the airflow at the door.
Yeah, and every time we try to open the window, but they'd keep bolting it shut until someone else comes in with an actual power drill just to open the window again. We were just fighting with whoever was bolting the window shut because there were people there.
let's talk to the department.
It's like Prison Break.
Yeah, I think
Like-
eventually, I think they did something really messed up to it. I think they cemented it or something.
Oh, it wasn't an actual FPGAs like drilled to the board that can easily be like unscrewed and like stolen.
Yeah, all the FPGAs are easily
Yeah.
stealable in the lab.
Yeah, I think like one or two of them got stolen in our year because someone
Okay.
literally just unscrewed it off and took it.
Yeah, no, it's just basically like the case is connected to the computer or like locked to the computer, but then the bolts are just connected or just screwed
You
in.
can disconnect it with a coin. You could have disconnected with a coin, but now it's a little harder to steal because the room's locked. So
Yeah, surprisingly like what do you call?
And also it would get caught on camera if someone tried to steal it.
No,
yeah, that's true. There's a bunch of cameras all over the place.
surprisingly about the VLSI room, the DOE department doesn't have the key for that lock. Or for the door lock.
So if it ever has to get locked, then
You're screwed.
okay, that's
What do you call, like they had a spare, like when I was like requesting for a key, they had a spare key, and then I tried it out, it doesn't work.
okay. That's bad. I
Yeah.
might need to change the locks on that.
And then they're like, so something to know.
All right, I guess that's everything, guys.
Thanks again.
Yeah, no problem.
All right.
Have a good weekend.
Have a good weekend. All right.
All right. Have fun, guys.
Yeah.
Thanks. Bye bye.